Perfect.
Okay, so hello everyone. Let's start the experimental method session for today. The first speaker is Professor Bruno Blais from Polytechnique Montréal, and he will be talking about discrete element method. Bruno, the floor is yours.
Just give me a second.
Yeah, sure.
Perfect. Okay, so I hope you all hear me correctly. So I'm Professor Bruno Blais. I'm going to be talking today about the discrete element method, and this is part of the series of articles in the Canadian Journal of Chemical Engineering about experimental methods. So you'll see DM is not an experimental method per se, it's a simulation method, but same but different, let's say. So, well, hopefully I'll be able to change slides. So DM simulates granular flow. It uses simple particle-to-particle contact models that must be calibrated, and it can accurately reproduce all types of granular flows. So we're going to be using DEM to simulate the flows of powder in drums, in uppers, and in other unit operations. It can also be coupled to computational fluid dynamics to predict what we call solid fluid flow. So using CFD-DM, the coupling of the two, we can simulate the dynamics of a fluidized bed, of a spouted bed, or for example, of pneumatic conveying. DM, as we're going to be talking about a little bit, is computationally intensive, and the simulations can require weeks of calculation using modern high-performance computing architecture using 1,000 core or even. So, powder is everywhere and granular matter is everywhere. 50% of the products sold worldwide involve granular matter at one point or another in the process. And 75% of the raw materials in the chemical industry come in the form of powder. This can take many forms and many shapes, but it's actually very important. So it's quite surprising that in a chemical engineering curriculum, we only learn about fluids, so gas and liquids, but we never really talk about granular material. But granular matter is everywhere, and it's ubiquitous to chemical processes. So granular matter is stored. For example, here we have an example of a grain silo used in the agro industry. It is transported, like using a conveyor. It is mixed. For example, here we have an example of a V-blender used in the pharmaceutical industry. And it can be, for example, heated. Here we have a rotary kiln. So all of the unit operation we have for liquid, there is generally an equivalent unit operation for granular material. For example, we could have a stir tank to blend the liquid. Well, the V-blender is going to be the equivalent, but for granular material. So what is peculiar about granular matter? Well, each particle that makes up an assembly of particle has a unique size, it has a unique shape, it has a unique surface roughness. And granular matter has a very weird rheology, per se. So a heap of particle can handle stress, and it does not deform readily like a liquid. So if we look at the bottom right, we have a heap of sand, and at the top right, we have water. Well, if I pour the water on my desk, it's going to spill everywhere, and we're going to have a very flat liquid everywhere. If I spill the powder on my desk, however, I will have a neat pile, and it's going to remain like this, and there's not going to be any flow. So there's going to be some sort of stress handling by the granular material. And this leads to very interesting phenomena that we encounter in the industry, such as the occurrence of a maximal packing fraction. And in a way, granular flow are always two-phase flows of powder with air in between. Vaulting phenomena, where we have, for example, bridges that can be formed in the powder, clogging, and size and shape segregation. So size and shape segregation is a very large challenge for the pharmaceutical industry. Here we have an example of this. So what we will see is, here we have two powders. The large powder is white, the small powder is black. And as we're going to be mixing the two powders, they're not going to mix and blend, but they're going to segregate and separate. So it's a bit like an exhibition of what we call reverse entropy. So you give energy to the system, and instead of getting more chaos or more blending, you actually get more order. And this is something that we observe a lot in granular matter and with granular material. And that is quite the talent, because imagine if you're blending two active components or multiple active components to create a drug in the pharmaceutical industry. And the more you blend, the less everything is mixed. Well, that's the challenge we face on a daily basis. So what is the discrete element method? Well, the discrete element method is quite simple. It's just applying Newton's second law for each individual particle that are in your granular flow. And the key point in this is, well, we have the sum of the forces equal the mass times the acceleration. But what is in red is really what is dm, and that is the contact forces. So how do we actually calculate the contact between the particles? Well, for this, we allow the particle to overlap. I will define what this is in the next slide. And using this overlap, we calculate the forces in the normal and the tangential direction. So what is this notion of overlap, which is quite essential? Here we're going to see it. At the right, the particle is going to come to the particle at the center, and they're going to enter collision. As they're going to be entering collision, this collision will occur when there will be an overlap, when the two spheres will be overlapping, and this will generate a force, and then the particle at the left will feel the contact, and it will move from right to left. So here, the view we got of the overlap was extremely exaggerated. In real life, in the real DM simulation, the overlap is going to be less than 1% of the particle diameter, but this is still the key idea. To allow for collision, we allow the particle to overlap. As they're overlapping, it generates a force, and this force is what drives the dynamic of the granular flow. And this allows us to handle multiple contacts at the same time. So most DM force models can be written in this very generic fashion. There are 4 components to the force: a normal and a tangential elastic force, and a normal and tangential dissipative force. And the key point here is you see these Kn, Kt, gamma n, and gamma t parameters. These are the contact force models that must be calibrated. And to calibrate them, we can either use the material properties, for example, the Young modulus and the Poisson ratio, but we can also do calibration experiments, such as, for example, looking at the repose angle and reproducing this in our DEM model. So this is a good example of a DEM simulation for a flow in the agro-food industry. So we have at the left the flow of powder in a flat bottom silo, and at the right we have a wedge-shaped silo. And we see that there is this angle at the top, and this is the dynamic angle of repose in this case, because there is motion in the powder. And we see that DEM is really able to reproduce this behavior, let's say, with very high accuracy, and it's actually quite efficient at this. So at the right, the flow contains about 500,000 particles. This is something we can routinely simulate in a day now using an appropriate computer. We can also use DEM in the pharmaceutical industry. So at the left, what you will see is a V-blender. So a V-blender is a unit operation often used to blend powder. You see at the left, we have the red powder and the blue powder. This is just used to see the dynamics of the mixing between the two powder. And as the V-blender is rotating along its axis, we see that the red and the blue powder are being mixed. What you see at the right is how the processors are moving as the particles are moving to ensure that there is efficient parallel computing in this case. So we can do the same thing for rotary kilns. Here we have the simulation of a dryer in which we have about 200,000 particles, and we're simulating the motion of each individual particle and reproducing the flow pattern. So with these type of simulation, we can predict granular segregation, we can predict flow rates, we can predict angle of repose, and multiple quantities of interest for our unit operations. So what are the uncertainties? Well, I said it before, contact models must be carefully calibrated, and we need a new set of calibration experiments for each new powder. And it's unclear which experiments are the most representative of most of the flow that occur in the industry or in many unit operations. External factors can play a role. If there is humidity in the room, the flow of the powder might change. And this is hard to take into account into the DEM model. So it's difficult. One of the last challenges, I guess, the accurate measurement must be available for the size and the density distribution of the particles. But this is less and less of a challenge now that there are adequate equipment for these type of measurements. So what are some of the limitations? Well, computational cost is one. Simulating over 1 million particles is computationally intensive. This is mitigated by the use of clusters or GPU, but it's still an active field of research. And in the simulations, we need to use very small time step values to accurately resolve the collision between the particles. It's a steep learning curve to learn how to use DEM. It's not an easy thing. There is not that many commercial software, and it's hard to just say open up something and start a DEM simulation. It's a field that requires a few weeks or a few months to get into, but it's actually quite nice because with this, we can simulate the majority of the granular flows that are occurring in the industry. So where is DEM going now? Well, as you saw in the previous movies I showed you, everything I showed what was with spherical particles, but actually most of the particles we work with in the industry, or multiple type of particles we work with in the industry, are non-spherical. So DEM is moving towards the accurate simulation of non-spherical particles. This can be either done through multi-sphere models, in which we use assemblies of sphere to represent non-spherical particles, or superquadrics, in which we use more accurate, more complex representation of the shape, but which is still a convex representation of the shape. And there are also other alternatives, which I'm not showing here. Another challenge is to make efficient use of high-performance computing, and this has to be done through the use of load balancing on clusters. Here we have an example of, this is some work that was published by my postdoc this summer, and this is an example of what we're doing, where we're letting the processors follow the particle to make sure that we're adequately using all the computational resources we have. And this actually enables us to do a simulation that would take a week in a day or two. So this is significant cost saving. It's also significant time saving, because what you once were only able to do in a week, now you can do in 36 hours, for example. So that's quite nice. There are other active areas of research. The coupling between DM and CFD is one. Phase change when we have melting and sintering, for example, in additive manufacturing processes. Multiphysics with DM, heat and mass transfer, and the taking into account non-contact forces such as liquid bridges or electrostatics. This is where DEM is going to go in the next 5, 10, 15 years. So there are multiple DEM software. I put 3 of them that are open source and 3 that are commercial. Lete is the one my group is developing. It's fully open source under an LGPL license. There are 2 alternative, Lights and Yade, which are 2 very, very nice open source DEM software. And there are some commercial alternatives for those who are more inclined to this or who want a graphical user interface. So finally, let's talk a bit about where DEM is used. DEM really originates from the geomechanics, let's say, part of science and a bit. And that's why we see keywords like granular material, behavior, soil deformation, sand. But it also has strong ties to the chemical engineering industry. And that's why we see the keywords CFD-DM, fluidized bed, flow. So these are CFB. Also, these are all chemical engineering related topics. In between, we have a bit more the model development, so the mathematical theory behind DM or the computer implementation of DM. And this is where we'll see modeling, validation, and things like this. And finally, the last part is more related to the physics of granular flow, so more from a physics department kind of perspective, where we have granular flow, dynamics, segregation, and let's say theory about solids. So DEM is really both, let's say, in the geomechanics community, in the chemical engineering community, and also in the fundamental physics community. And I think that's it for me. So thank you very much for listening to me. And I'm always easily reachable by email or through the CCEC platform. So feel free to reach out to me if you have any questions.
Thank you very much, Bruno. It was very insightful. Do we have questions from the audience? Otherwise, I have a question myself. I don't see questions.
Yeah.
But
I would have a question, but it's in person. I don't know if people on Zoom can hear me.
I'll read.
Okay. I was wondering, because you were talking about using GPU instead of CPU to ease the load. I was wondering, if you're doing memory-intensive tasks, how would GPU computing work? Because you would have less memory, no?
So the question from the audience is, how does it work when we transition to GPU in terms of memory consumption or memory usage? So DM is not that memory intensive. So like, let's say a simulation with 100 million particles, if we simulate it over, let's say 10 or 20 nodes, we're not going to be using the full memory of the cluster. So it's not that memory intensive. So we can actually manage with GPU, but the issue is the size of the problem. So if you want to do realistic DM simulation with, let's say, a few million particles, you cannot do single GPU. You need to go to multiple GPUs, and multiple GPUs is difficult because then you need to couple your GPU, let's say your accelerator on your node, and then you need to do multiple node communication through MPI. And this is a bit difficult to achieve high performance on, because in DM we do multiple very quick iteration, just like in MD, in molecular dynamics. So communication can become quickly a bottleneck. You know, for example, in Lete, we work very hard to minimize the number of variables that are stored on each particle to minimize the communication intensity. And this enabled us to gain like 20, 30, 40% additional performance. So it's a challenge, I think. Single GPU is easy. Multiple GPU is extremely challenging. And this is a paradigm I haven't really seen yet.
Okay, thank you.
okay, we still have time for my quick question. I was wondering, how do you simulate, like, what are the parameters that you have to take into account when you simulate irregular shapes?
Okay, so simulating irregular shape can be done through 2 ways. Either you simulate the irregular particles using spheres, and you use friction models to model their non-sphericity. And if you want to model like directly the irregular shape, then you would have to have like a CAD of the irregular shape or a analytic description of the irregular shape, and then input this into your DM model. The issue is the contacts. Particle-particle contact detection and contact resolution when the particles are non-spherical are significantly more expensive. We're talking about 10 times more expensive. So a simulation that could be done with 100 million particle could most likely be done with 5 or 10 million particle if you were to transition with to non-spherical particles. So either you model it through parameters, or either you take it into account by really modeling the shape itself, deep down in the DM model.
Okay, thank you very much. Thank you, Bruno. So next speaker is Ali. I'm sorry, I hope I will not mispronounce your surname.
It's good enough.
Seifitokaldani.
Yes.
He will be presenting, so he is from McGill University, and he will be presenting density functional theory, DFT. I think you were able to share your screen.
Sure.
Okay, great.
So, all right. Okay, should I start?
Yes, whatever you want.
Okay. Hello, everyone. Good morning. That's a pleasure to be here and presenting the work which is published early this year. The work that I'm going to present is density functional theory, again, in the series of experimental methods in chemical engineering. And it was a good collaboration between McGill University and Polytechnic Montreal. And McGill side, my students Hasan Al-Mahayni and Xiao Wang work on this paper. And at Polytechnic, Professors Harvey and Professor Patence work on the paper. So before jumping into the details, I guess it's good to provide the highlights of what we have done in this paper. We have provided a very short overview of what's the fundamentals behind the quantum mechanics and specifically density functional theory and how it evaluates the electron density and consequently energy of a chemical system. And after that, we showed that DFT can provide insight into both bulk properties and surface properties of a material. For bulk properties, it can be mechanical and elastic properties like a bulk modulus, or thermal properties such as heat capacity and thermal conductivity. And for the surface properties, we start with surface energy and then binding energy for adsorbents on the surface of the adsorbate. And after that, we show how we can calculate the chemical reaction energy diagram, especially for the surface reactions. Then we show some applications for material discovery, specifically for finding a new catalyst, for battery material, photovoltaics, and electrochemistry. And we also discuss about the challenges which are facing currently for DFT. So this is scary, I know, but whenever we talk about any chemical system, especially many body system, when I say many body system, it's not only one part, it has some different spaces. For example, for one atom, we have a nuclei, and then we have the electrons moving around it. So in classical mechanics, the energy of the system is always of interest. And to calculate that, we include both kinetic energy and also potential energy. When we work in small size in the atomic level, then this energy is not directly obtained by calculating the kinetic energy and potential energy. We need to define the Hamiltonian. And after that, that Hamiltonian, which is an operator, will be performed on a specific function that I'm going to talk about that to get the energy of the system. So Hamiltonian, again, includes some parts related to kinetic energy of the nuclei, kinetic energy of the electrons, and then interaction between the electron nuclei, and nuclei. So overall, you see this is an operator. It's not a scalar variable or a scalar property. So we need to apply that operator on a function which is called the wave function. So this wave function has no physical meaning by itself. Although it's a square, will give us probability of finding a particle or an electron. That particle can be an electron. So at a certain time, at a certain position, and with a certain velocity. And this, to obtain the energy of that system, that many-body system, we have to solve the Schrödinger equation. So well, there's a long story behind that, where it comes from, why it's viable and we should use it, but I'm not going to discuss about that, and we have not even discussed it in the paper. But the thing is, we need to solve such an eigenvalue equation to obtain the eigenvalues, and the eigenvalues are the energy of the system. So, and the wave function that I taught can be even simplified a little bit more and divided into two parts, including the function which describes the nuclei at certain time, at any given time, and then the electrons kind of position. It's not, as I said, it's not exactly the electron position, but it's a function that describes the electron position. Anyway, my point is that this is the point that chemical engineer students, especially without any backgrounds in quantum mechanics, just freak out. They say goodbye to DFT. And that's exactly where we wanted to have a small contribution and let the students know that they can still have a good use of DFT and calculate a lot of properties of their interests without even having any background in quantum mechanics. That was the main objective. That was the main motivation to write this paper. So what we did, we basically walked the students, I mean the readers overall, but our main targets were grad students and senior undergraduate students interested in DFT. We showed them that what they need in general to run a DFT calculation. So it doesn't matter which kind of code software they are using, but in general, they need two types of input files. One file, which can be divided into several files itself, but includes the parameters, main parameters. And these parameters can be a very long list, but we just discussed the most important ones, such as cutoff energy, the K-point sampling, pseudo-potential, basis sets, exchange correlation functional, and few other convergence criteria. So these are the parameters that we need to provide. Of course, having some background in quantum mechanics, especially if you are working with the crystals, then the background in solid state would be very useful to understand what's the K-point sampling, what's the pseudo-potential, etc. But even without those, I have undergraduate students that they get trained within a month and they are able to run DFT computations. And over time, they understand the physical meaning of each parameter. So this is what they need to provide. And after that, the second category of the file, which is usually just one file, is the geometry file. So with that geometry file, we provide information about how our many-body system looks like. So by having this information, we again walk readers through the steps. The first thing that we need to run, or we run in DFT, is a single point energy calculation. The single point energy calculation basically is just giving a geometry to the DFT code. Doesn't matter if that geometry is a real geometry, is that far from real, and then just ask to calculate the energy for that system. This is the basic thing, and I would say the most important thing that the DFT does for us. So you can give, let's say, a crystal, or let's say a unit cell, which the lattice parameters are not even accurate, and then calculate the energy for that. This can be done easily through the DFT. But the next step is going beyond that and try to optimize the lattice parameters, for instance, and then make we call it a relaxed system. So let the system to obtain the real lattice parameters. For that one, we optimize geometry and the unit cell. So this is the next step that we usually do in DFT computations. And whenever you have a system which is already optimized, then you can calculate other properties. These properties can be like electronic density of a state that you see a few examples here, or band structure, and etc. But we didn't stop there. So we walk reader through all these steps, how they can actually do these calculations. We show them in the paper. But after that, we go to some specific application that I thought it would be easier to just use the paper itself in this presentation to talk about that. So as you see in the application part, we start with the bulk properties of materials, specifically bulk modulus and elastic properties. So here is an example that we say that if we are interested in bulk properties of, let's say, cubic system, and if this cube here in the center is the one which has a real lattice parameter, which is already optimized and relaxed, then to calculate the bulk modulus, we have such a formula here. The bulk modulus is the volume multiplied by the second derivative of the energy based on the changes in the volume. So this is what we have from classical mechanics. It's not the quantum mechanics formula. So then how we can calculate the second derivative? We just need to obtain the energy for the system at different volumes and then take the second derivative of this energy to obtain the bulk modulus, as simple as you see here. So for that, we start with the let's say cube that is already optimized, and then we shrink it or we expand it. And after that, for each one of them, we just run a single point calculation. So each of these single points are the basic DFT calculation that we obtain the energy for. And then easily we can get the second derivative of this curve to obtain the bulk modulus. So we go beyond that. We say, okay, this is about the cubic system. What about if you have a complicated system? And for a complicated system, then we need to provide a stiffness constant, or it can be also related to the elastic coefficients. So for that, again, we need to look for some formula, some physical formula in classical physics or mechanics, and then after that, try to find a way in DFT to calculate those energies. And everything is about the energy. This is what I always say to my students in DFT. Everything is about the energy, and all the simulations are same. You just need to have the right path to follow those calculations. So here, what we do is basically we have that formula. You just need to again deform the cell, and all those the deformation formula are given here. How the cell can be, the unit cell can be deformed, and then the relevant energy calculated to obtain the elastic parameters for this specific problem. So this is about the bulk properties, and after that we move on the surface energy calculation. For the surface energy calculation, again, we just describe it as simple as breaking down a unit into two parts, and then the energy in the surface can be calculated simply by the difference between these two sides of the arrow. So here you have some energy, here you have another energy. The difference will give us the surface energy of the system. So the surface energy calculated, and after that we talked also about the defect formation and surface reconstruction. So I just want to make it quick, so I'm not going to describe everything, but some basic things were calculating the adsorption energy. And when we compare the formula to calculate the adsorption energy, which is given here, we realize that it's exactly the same formula that we use to calculate the surface energy, and the same formula that we use to calculate the reaction energy, or the same formula that we calculate to obtain Gibbs free energy for any phenomena that we have. And that's true. We always use the quite same formula to run the calculation. So I just make it short here. We talk about different systems. We walk the students about even how we can run the molecular dynamic simulations or quasi-harmonic approximation to calculate the energy at elevated temperatures and pressure. And eventually we give some example about the like catalysis chemical reaction and also electrochemical reactions that are shown here. All right, so I switch back to my PowerPoint. So with that, we have also at the end, we just talk about the uncertainty. What are the sources of inaccuracy in DFT calculations? We talk about them. We show that computational time is still a big problem for us. We cannot really handle large systems with more than 1,000 atoms. It's real difficult. And then calculation at higher temperature, again, it just comes with some approximation. It's not as accurate as ground state calculation. And again, just replicating the experimental condition is not yet there. So we still have a lot of work to do. And I'm not sure how much time I have. I can see the time. So, oh, okay, it's quite over, I guess. So I can stop here. But we also discuss about the future or like a perspective of the DFT applications in future research in chemical engineering. Sorry, it was longer than what I was expecting. And I would be happy to take any question.
Yeah, thank you very much, Ali. Do we have any question from the audience? In Polytechnique? I don't see questions. I do have a curiosity.
Sure.
How much time does it take to process a system of 1,000 atoms?
So 1,000 atoms is very difficult. It depends on your computational resources. Let's say what we use is compute candidate clusters. So normally we use, let's say, 4 nodes, and each node include like 32 CPUs. So let's say around 100 CPUs. For 1,000 atoms, if it's already close to the relaxation, it's already optimized, it might be okay to run it in half a day. But if it is far from the optimized system, it may take a month. It really depends on the system, how far you are. So we have different systems and they take different times.
Okay, thank you very much. The next speaker is Ergus, one of my colleagues from Polytechnique Montréal. He's presenting in person. And he will be talking about the Monte Carlo method.
Okay, can everyone hear me?
Yeah, perfect.
Okay, perfect. I can start now. Okay, hello everyone. This morning I'm going to talk about Monte Carlo applications in chemical engineering. Very briefly, the highlights of my presentation will include some introduction to Bayesian approach to engineering problems. Then I will talk about the broad variety of applications we can find on Monte Carlo methods. I will touch then on uncertainties of these methods, as well as introduce a case study in chemical engineering, and in particular in a biological system. So very briefly, I wanted just to show the big names that actually worked on developing these type of techniques. So we start from Bernoulli with a theory of large number, then followed by around a century later from Laplace, that developed the first Monte Carlo experiment, documented at least, where he just threw some needles and he was able to evaluate pi. Then we have Enrico Fermi, who was evaluating, using Monte Carlo to evaluate the transport of neutrons in nuclear reactions. And finally, we have Metropolis and Ulam that gave the name to the Monte Carlo method we know today. So far, as you can see, the modern applications are all related, including the Metropolis one, to nuclear engineering. But from the 80s, we see application in other fields, as I will talk about later on. Now, in engineering or same problem, we have uncertainties that is carried out from initial state, from input data, as well as from parameter. So if we feed these to our model, Y, we will get a model output with whom we can calculate our parameter estimation, evaluate the uncertainties, and a sensitivity analysis. Now, the way a Bayesian approach follows is the evaluation of a posterior distribution of these model output Y, given a prior information we get from our system. So to give a simple example, to familiarize everyone with the Monte Carlo, is Markov chain Monte Carlo, short for MCMC. And where we have, first of all, an initial parameter that we give as initial guess. Then we have a new trial position, theta star, the depends, as you can see, from theta k minus 1, which is our previous value of theta. And depends also on a very important factor, which is a jump delta theta, about which I'm not going to talk in this presentation. And afterwards, we evaluate a metropolis ratio. And this will tell us whether the new trial position is giving us a better probability of our output or a worse probability. In the first case, we accept the new value. Otherwise, we reject and we go back to the previous one. So on the right-hand side of the screen, you can see how this looks like in the case of a bivariate unit normal distribution. In this case, I have a chain of 5 chains and a sample of 20 times. And this is approximately what it looks like. And you can see how after several iterations, we converge to a mean of 0, 0 for both parameters. And here is how the chains actually appear. Now, in this case, you can see that each chain does not have 20 samples because many of the samples were rejected. So how does this look in case of 300 samples, for example? It's something like this. So you can see it's actually a quite good approximation of this bivariate unit normal distribution. AR is the accept and rejection rate. So 46% of the samples were accepted in this case. Now, about the applications, the quantity of application is really very broad. So we can see that we have applications in economy, human behavior and decision making, for example, applied to transportation and so on. But let's focus on the chemical engineering side, and we can see that looking at literature, uncertainty, algorithms, and now everyone knows about MCMC, are very relevant keywords that we find. Then we see a lot of application also related to density functional theory and kinetics. So, and as we talked before, we have also energy application, especially in the nuclear field. So we have radiation, radiotherapy, as well as medical application like cancer treatment. And finally, we have the correlation, let's say, connection between algorithms and density functional for the development of molecular dynamics. And this touches very relevant topics today, such as carbon dioxide and metal organic frameworks. So about the uncertainties we have with Monte Carlo is inaccuracies. By this, what I mean is that we are not able to guarantee the optimal solution of a parameter estimation, for example, but we get very close to that. Then the importance of calculating both uncertainty and sensitivity analysis. So this is a very relevant point provided by paper Saltelli et al. In 2019. And he actually investigated that in hundreds of papers, 50% of those papers did not provide either uncertainty analysis and sensitivity analysis, or neither of them. So making, without giving relevant information about the quality of the model that the people use. Then we have a issue of computational requirements. Sometimes we may require very many simulations to have a decent evaluation of our parameter. And finally, this is a key point, algorithm efficiency, which is actually the also part of future works related to Monte Carlo. And here about algorithm efficiency, I wanted to show also what happened in the case of the previous problem we saw, the bivariate simulation. And you can see how in a very few sample size, for below 100 for sure, we have that we go from a mean of 10, minus 10, minus 15 to the actual mean of around 0. Then I would like to present a couple of case studies. I will start with ammonium oxidizing microorganisms. So this is actually part of a twofold reaction. We have ammonium oxidizing first and nitrite oxidation to nitrate. I'm removing that part from our equations, but we can see that the growth of our microorganism, AOO, depends on a maximum growth rate, Mumax, and then we have some affinity coefficient, Ks and Ko. Then we have a concentration of chemicals within the system that affect, of course, the parameter estimation. As a parameter, we are considering 4 of them: the yield of the biomass, the Mumax, and the 2 coefficients we discussed earlier. So we repeat a Markov chain Monte Carlo sampling on these parameters. Here you can see how the sampling works, and in this case as well, we of course reject part of these samples. After we do that, we can evaluate the uncertainty analysis. So we see how parameters actually affect our output variables. And on the right-hand side, we can see, for example, that there is a hyperlinearity between some of the parameters, where you see, for example, linear correlation between them. And so this is telling us that our output variables on the left are giving us a quite accurate result by even modifying the parameters as we see in ammonium, for example, oxygen and nitrate. But there is a larger uncertainty in the evaluation of the biomass concentration. The same, and then following, we can do a sensitivity analysis. And to do that, we evaluate the derivative of our function in comparison with every parameter we have. And this will tell us how each parameter actually affects our function. So some parameters have a stronger effect on it and others less, as you can see on the right-hand side of this slide. And we can then rank which parameter is actually affecting more our function. And this is presented on the left-hand side of the slide. So finally, we can evaluate the parameter estimation. So we evaluate the mean from all our simulation, accepted ones. And we can evaluate standard deviation as well as the Monte Carlo error. So following this, I wanted to show also how would another algorithm look like. On the right-hand side, we develop also a sequential Monte Carlo method. So differently from the previous case, we have that the data is introduced to the system at a step-by-step basis. So the system is updating the parameters at each time step. So this is a kind of inline modeling. And we can see if we run the, okay, we can see that there is a drop in uncertainty and in confidence after a few steps. And on the left-hand side, we can see also how the distribution starts from approximately a uniform distribution and tends to becoming approximately a normal distribution. So finally, I wanted to show also a more complex problem with lactic acid bacterial fermentation and used for yogurt production, for example. And to do that, we again simulate over time, so still in dynamic mode, and we can see how the uncertainty is dropping, especially for the output variable on the right-hand side, which is the biomass concentration and lactose and lactic acid. So to conclude, I want to emphasize the importance of uncertainty and sensitivity analysis in a model. Monte Carlo methods can do that very well. And the applications are very broad, so I suggest always to look also at application outside engineering and science, and those can be applied as well to our systems. And finally, the application of new and development of new algorithm is the key for future development of these Monte Carlo methods. With that, I'd like to conclude. Thank you, and I'll be happy to take any question.
Thank you very much, Ergus. Do we have questions from the audience? I don't see questions online. Well, I do have a question. What are the limitations of these Monte Carlo method?
Sorry?
What are the limitations of the method?
Okay, so the limitation, I would say, mainly on a computational point of view. So practically, sometimes you need a very large sample to get an accurate estimation of some parameters. So that will be probably a big limitation. But generally talking, the way you develop the model, so understanding the model you have is probably the key factor. So I will say, yeah, that is the...
Okay. Okay, thank you. Federico has a question. Fede, go ahead.
So, Ergus, can you hear me?
Yes.
Yes.
Thank you. Thank you for your presentation. My question is more a curiosity. In fact, why the user should prefer a Monte Carlo compared to general nonlinear regressions to estimate parameters?
Okay, yeah, so that's a very good question. So there is no actually a good approach to follow, but yeah, some people may prefer following a frequentist approach, as so-called, which is also working fine. I mean, some scientists prefer to look at parameters as depending on the data they collect directly, but Bayesian approach is more like looking at also how the prior distribution of our system looked like. So yeah, there is no exact answer to that. So there is some people prefer to follow a frequentist approach rather than a Bayesian approach, but they both can give a good result. So I don't know if I answered the question.
Absolutely.
Okay.
Thank you very much, Ergus.
Thank you.
So please welcome the next speaker, Federico Galli from Polytechnique Montréal, actually University of Sherbrooke now, and he will be presenting a process simulation. From Polytechnique, can you please stop the screen sharing? Thank you. Fede, go ahead.
Okay. Do you see my screen and my presentation?
Yes, perfect.
Okay. Thank you for the beautiful introduction. So my name is Federico. Today, my presentation is about process simulation, with particular reference to steady state simulation. The article is already published in the special issue, and I wrote it in collaboration with Nooshin, Jacopo from Polytechnique, Francesco Rossi from Purdue University, and Professor Carlo Pirola from the University of Milano, and of course with Gregory Patence. So when do we use process simulation? We use it, most of us use it every day to solve enthalpy, energy and mass balances for single unit operation, or for the whole flow sheet to solve a total flow sheet. For steady state simulation, our final results will be time independent. One of the pre-requirements for a good simulation is the selection of the best thermodynamic method for component mixture and for property estimation. We will see some examples after. We will also briefly talk about recycles. Most of the errors and solution not found originate from recycles, indeed. And finally, why do we need process simulation in our engineering life? well for process design, for process optimization, but also as a tool for research and teaching. So a little before we talk about thermodynamics. Thermodynamics, this is a very important selection to set up correctly our simulation. For a student point of view, this equation might seem a little bit obscure and complicated, almost impossible to understand. And what happens is that 99% of the cases, the user selects the Penn-Robinson or a group estimation model to simulate their data. Let's do a little bit of clarification very fast. In general, there are two main thermodynamic approaches. One uses equation of states to calculate fugacity coefficients. And you will see, for example, in this slide, a general cubic equation of states that groups the Penn-Robinson or SRK equation. And there is also the gamma approach. For example, here reported the non-random to liquid equation that calculates the non-ideality of a solution. For example, for non-associating components below the critical point. In our paper, we put a table, and I reported here, with the main advantages and limitation for the phi approach, equation of state, and the activity coefficients approach. As a general suggestion, check always in the literature the models that they employ for their system, and double check always the data simulated, also the data of the papers. So after having selected the thermodynamic model, the user proceeds to build the flow sheet and run the simulation. So most of the commercial software, in this slide, you can see Pro 2, which is from Aviva, but the Aspen Plus, they work in the same way, employs a modular approach, meaning that they solve unit operation one after the other, unless there are complex cycles, there are algorithms that optimizes the solution order, but let's say that they solve one unit operation after the other. But what happens when we generate the flow sheet in the simulator? Well, what happens is that from a stream to a reactive distillation unit with multiple outstream, the system builds a system of nonlinear equation that the simulation needs to solve. Depending on the unit operation, the equation may be algebraic or differential algebraic. For example, PFR are differential algebraic. In this slide, G is a general balance equation, while X is the process variable. Via an iteration algorithm, the simulation finds the vector of X that satisfies all the balances. So before the user clicks on the run or solve button, depending on which software are you using, they should select the solution algorithm. Most of the times, and these I also do it most of the time, I just leave the default option to solve the problems. But here, let's try to give at least an idea how do the two main algorithm works. So Newton-like methods calculate the Jacobian matrix, which is a matrix that stores all the first derivatives of our function for all the variables, and proceed in the direction of the derivative to find the local minimum. In the end, is the Newton resolution algorithm. These methods are faster than fixed point, but are very sensible to initial guesses. Use them when you have a little amount of recycles, and when these recycles are not nested, so they are not recycled in recycles, loops. Also, pay attention to problem initialization. On the other hand, fixed point methods reformulate the generic system that we saw in the previous slide in this form. The algorithm calculates the value of the function at the initial guesses, select a relaxation factor that we are not going to discuss in this presentation, but there are also acceleration methods you can check the paper. This was Francesco contribution. Is a machine on this, and calculate the next iteration variable. The algorithm stops when the vector x where the vector x of the iteration +1 is similar enough, depending of course on the tolerances, to the iteration before. So Voss viewer generated a text map from the most recent articles containing process simulation, either in the abstract or in the title. When you see these kind of maps, the bigger the cycle, the higher the count of the specific keywords, while the vicinity of the cycles means that there is close interaction between the words. So the main, sorry for that, the main word is Aspen Plus, which is the most employed software in chemical engineering. Closely related, we have techno-economic analysis and economics. This because one of the main objectives of process simulation is to estimate capital and operative expenses. In our article, we give an overview of the most employed methods to calculate cost. So I refer you to the article. The green cluster related to design and sizing of unit operation. In particular, recently, most of the work has been dedicated to reactive distillation and biofuels. Process simulation helps engineers also to optimize processes, to improve efficiency, and eventually, the yellow cluster is dedicated to new works that deals with CO2 reduction and emission controls. The software never makes error when solving a mass balance, okay? Unless we put impossible specification, but the software simply minimizes a set of vectors, as we saw. So the errors always originate from the wrong user inputs. Here, I report, for example, an error in the estimation of vapor pressure of phenol, okay? Let's talk about phenol, so pure component properties. Vapor pressure is a pure component property and depends only on temperature. The property is calculated usually by the Clausius-Clapeyron equation. What I did here is that I took a random components, literally it was the first one I checked, phenol, and I took the database component, the green line, and I compared the vapor pressure versus the literature, okay, versus the database. Then what I did is that I build phenol using the unifac groups, and I use the Jacopo method to estimate the vapor pressure of the component. This is a method that works more or less as unifac. So what they do is that they regress a lot of data from the literature, splitting the molecule in different groups. For example, the CH3, CH2, etc. So they can, in this way, without knowing the property, you can simply build your molecule and estimate the properties. But what happened is that, as you can see here, in the red line, overestimates the vapor pressure and a lot. Even though, and also even though phenol is a quite common and normal molecule, okay? So the more complex the molecule, the bigger the error. However, these group contributions are not the devil, because, for example, in this very example, the heat of vaporization, which is the slope of the line, is kind of well estimated. However, always check the property estimation. If you have the component in the database of the software, use it. Don't estimate the property at random. And when you have to do it, try to check it versus the literature. Here is a second example. Here we are talking about a binary system, okay? So thermodynamic model to calculate vapor-liquid equilibrium. This is the diagram of the binary vapor-liquid equilibrium of the system water and acetic acid. The distillation of this mixture is important in bioprocesses and also in the terephthalic acid synthesis. The diagram reports the liquid molar fraction of water on the axis versus the molar fraction of water in the vapor phase at the equilibrium on the y-axis. Both the component properties were taken from the database. So in theory, all is good. However, if we simulate the equilibrium with the uniquark model, the red line, we see that the system forms an azeotrope, more or less here. Do you see my other pointer? More or less here. Okay. Around the liquid mole fraction of water of 0.85. This azeotrope does not exist in nature. So how do we avoid this? Because we need to consider the association of the acetic acid in the vapor phase. And the uniquark model, which is a gamma model, does not consider non-ideality of the same molecule, considers non-ideality of different molecules. So in this case, the Heidenau-Koller calculates the vapor association, calculating the fugacity coefficient. So also, when components in the database are available, the user should always verify when possible the simulation with experimental data. Otherwise, error may occur. And in the case of the binary distillation, having or not an azeotrope in your system changes dramatically the design and the cost of your equipment. So in general, to avoid errors, always try to initialize your variable with a good first initial guess using experiment or literature data. Do your overall mass balances by hand. Do not trust blindly the results. If they are unnecessary, avoid loops. For example, if you do not care about the heat integration, avoid adding heat exchanger or control loops. If you have a recycle, solve your flow sheet with open loop first, then manually close it and run again the simulation. In this case, the simulator stores the steady state values of the previous iteration and uses as the first guess, which is always best to do. So a little bit of perspective for process simulation. Process simulation is an interesting tool also for teacher and for teaching. Nowadays, and this is true, plant operators are trained in a virtual environment that simulates the overall plant. A dynamic simulation calculates the consequences of an operator action, or can generate process deviation to train the operator to react. The picture that you see is taken from the program iSim, which is a pilot program that we started at the University of Milano to teach students how to work in a real simulated environment, very close to reality. On the other hand, if the thermodynamic model is well set, the user is able to calculate the operating variable boundaries or reactant maximum conversion. In this picture, for example, in the figure you see the figure of thermodynamic, so maximum methane conversion, and obtainable hydrogen to CO ratio for the catalytic partial oxidation of methane at two different temperatures. The simulator also identifies which oxygen to methane ratio cokes start to form. So to do all of this, the computer took less than 8 minutes to complete the simulation. So to conclude, with process simulation, we can estimate cost, improve heat recycle design, size the unit operation, and train the unit generation engineer. Thank you very much for your attention, and I'm ready to answer your question.
Thank you very much, Fede. Do we have any question from the audience? From Polytechnique, I don't see anybody anymore in Polytechnique.
Yeah, yes, I do have a question.
Oh, okay, go ahead, Jacopo.
So, hello, Fede, thank you for your presentation. So my question is, how do you think we can integrate process simulation with other experimental, one of the other experimental methods we've seen in these days?
Oh, but that's a good question, Jacopo. Thank you so much, because itself a process simulation like the presentation of Professor Ali doesn't look like an experimental method itself. But if we integrate a process simulation in the last graph that I show you about system boundaries, etc., you can use process simulation to define your experimental design. So you know that you cannot exceed with a certain, for example, oxygen to methane ratio. Otherwise, you will very likely produce carbon. Of course, simulation gives thermodynamic formation of carbon, and experiments are something completely different. But for example, it can give you system boundaries. So someone can design their experiment in the good range. This is just one of the examples.
Thanks. Thank you.
Thank you very much, Fede. Our next presenter is Professor Gregory Patence, the creator of these experimental methods series in chemical engineering. I hope he's ready with this presentation. I don't. Gregory?
I am here.
Okay, great. So please welcome Professor Patence, and he will be talking about fluidized bed reactors.
Yeah. Abruptly. Okay. Sorry, I got mixed up with the rooms. Thought it was A404, then I went to B406, and then I called. And then... Yeah.
I think. Oh yeah.
One little.
Oh.
Okay.
This one.
Yes. Okay. So. Okay, you guys see it? You guys see it? Did you
Yes.
see it, Galma?
Yes, I can see it.
Okay.
Perfect.
So again, you might ask the question, what does fluidized bed reactors have to do with experimental methods? Well, I guess it's kind of obvious. You know, you develop kinetic data with fluidized bed reactors. So the question that I'll start with the highlights. So fluidized beds in general are for exothermic explosive reactions. Okay, the difficulty and challenges with fluidized beds are scale up, attrition, and there are commercial challenges. And what's interesting, fluidized beds are used when fixed beds don't work, and so usually it's very difficult chemistry, and that's sometimes why it has a bad reputation. But it's only doing the typical stuff. The problem right now is when people talk about fluidization, do reactions in it, they don't tell us what the particle characteristics are. And if you don't tell us that in detail, then we can't understand what you're doing. And this is a complaint that I have, and this is one of the reasons that this article is there, is that tell us what your data is. The things that we use to actually analyze the, let's say the fluidization characteristics, pressure drop, optical probes, image velocimetry, and those are, you know, to understand what is going on. Now, what I suggest is that, you know, chemical reactions are the best way to actually understand. And these are gross methods, and people have concentrated on it instead of looking at the details, okay? And then what do we want to look at is, again, bad reputation. People talk about fluidized beds as backmixed. Well, that's not true. Okay, solids are backmixed and not necessarily perfectly backmixed. But when you're using the fluidized bed as a chemical reactor to understand kinetics, that's where the beauty is. And now you got to understand, how does a model, how do simple models impact your kinetics? And so we'll talk about that. I advocate fluidized beds as a means to measure kinetics, okay? And the reason I think that's interesting is that if you have complicated kinetics, you have deactivation. If you have solids buildup, carbon buildup, if you have changes in oxidation state, a fixed bed will have profiles, whereas in a fluid bed, everything is backmixed. The only thing that's not as well known is a gas phase. And so what is the contribution of the gas bed? So to talk about fluidization in general, this is the powder classification. You've got A, B, C, and D, Gelthart's classification. So typically for reactors, fluidized bed reactors, for catalytic reactions, we want irritable catalyst, okay? Bubbling mode is more like for combustion. Spoutable beds, that's for some drying. And then cohesive powders are really what's the most important aspect of chemical engineering is nanoparticles, and then you're talking about cohesive powders. So examples of irritable powders are milk powder, FCC. Then in sand are bubbling type wheat, coffee, beans, drying is for spoutable. And then you've got the cohesive flour and cement. So these are the range of different particles that you're talking about when we now in terms of fluidization rates, just to give you, what is the fluidization rate? So low gas velocity, you start with a fixed bed. You increase the gas velocity, there's a relationship between velocity and particle characteristics. So as you go higher DP, you go to Gelthardt D powder, smaller DP, you go to Gelthardt C, okay? And so we go from bubbling, smooth, channeling, and that's gas velocity, let's say of 0.01 meters per second, but of course, if you've got the big particles, then it's a higher velocity. Spouted beds operate from 0.1 meters per second and above. Turbulent fluidization is really 0.6, 0.5 for Gelthardt C powders, A powders, to 1 meters per second. And then you get into the fast fluidization range. And then finally, in pneumatic transport. So when you look at this, you say, okay, what am I going to be doing? How are these, where are these fluidization regimes in industry? Well, what we've got is the DuPont's circulating fluidized bed. And in fact, almost all of these regimes are in the fluidized bed. So you've got a fixed bed, probably in the standpipes of your dip legs of your cyclones. You've got turbulent regime here in the fast bed. You've got the pneumatic transport in the riser. You've got bubbling regimes in the strippers. So what happens is when you have a complete fluidization system, you have all of the regimes. And so that's something that people don't necessarily understand. So this is the regenerator that was 4 meters in diameter. We'll talk about that in a second, okay? So the riser here is here, and then we had to add some additional height. It was a $5 million project, the biggest crane in the world, to add for a lift of 5 tons to put a heat exchanger above because we were having problem with temperature excursions. So in terms of fluidization, the literature, what are they looking at? Combustion, CO2 capture, kinetics, that's the highest. Then we're looking at simulation, particles, reactors, behaviors, just looking at the circulating fluidized beds. Then we're looking at pyrolysis, applications of gasification, steam, hydrogen production. And finally, in along all of that, we're looking at systems, performance, coal. So those are the regions. It's probably basic chemical engineering. It's not necessarily the immobilized cells that I was talking about. And then you've got the biomass and bio-oil, okay? So the most simplest test you do, and the first thing is you test your minimum fluidization velocity. So what I had to do is I had 15 students that weren't trained to do it, and they got this data. And you don't report more than 1 significant or 2 significant digits in fluidization because there's so much variability. So we have these tests, you look at the intersection, and that's how you get your minimum fluidization. But that value is variable. And then here we've got sand. And again, you've got this huge variability of the minimum fluidization velocity. So when you're reporting that, you've really got to be careful. So UMF is one of the basic parameters that you have to talk about when you're working with fluidization, okay? And then here are the others, okay? So you've got bulk density, you've got particle density, you've got skeletal density, you've got the theta, the angle of repose. Then you've got to talk about the particle distribution, surface area. These are critical. And this is, for example, FCC versus SAN. And so not only have you got to talk about the actual value, but you've got to talk about the standard deviation. Okay, so we've got 2.2 millimeters per second, plus or minus 0.7 for these 15 people. And then we've got 25 millimeters per second, plus or minus 5. So there's a huge range. And so when people talk about give 3 significant figures on a correlation for solidization, it's just like they're not serious. Okay, so here is the particle size distribution and shape. You can see that, okay, FCC is round. No, it's not round. You know, the question is, what is its shape factor, okay? And then, of course, you've got the sand. Sand is not round, okay? So it has, you know, what are the implications of shape in DEM? It's not necessarily very clear. And I think it's an interesting area of research. So I'm coming back to the first slide where we're talking about the regenerator. And why do we are interested? I mean, is everything known about what's going on in the reactors? And what Steve Jordan did is he took samples in the regenerator, and this is the oxygen. You see that we got a 4-meter diameter, and we have solids coming in from the side here. And then you can see that there is less oxygen right here where the entrance of the solids are. And there's more oxygen here on the edges. So what we're looking at is poor distribution. Now, and if that was the only data, you know, well, maybe it's just an experimental error. But then we looked at CO2 and the absolute opposite. So we have a lot of CO2 on the edges and a lot of CO2 in the middle and less in the edges. So there is problems in fluidization at the industrial scale that you have to worry about. So what we also did was we looked at, okay, as an experimental reactor, we had FCC catalyst in this reactor. We had a mass spec that was measuring 2 hertz frequency. And what we're looking at is describing just the overall hydrodynamics. And so we've got this axial dispersion model, and the Peclet number is a characteristic. High Peclet number, fixed bed, plug flow, low Peclet number, completely backmixed, okay? And so here is our impulse study. We change from air to argon and look at the oxygen. And you can see if you're just looking at the mass spec in the lines, it's very, very, let's say, steep, and it's a pulse. It's a very good pulse. Now, if you put the empty bed in here, then you can see that there's dispersion, that it's not as flat. And so things are mixing and there's laminar flow and things like that. The question is, what happens when you put solids in? Where does the solids come? When you put the solids in the bed, what happens to the curve? Well, it shifts to the left because the solids occupy space, so it comes out faster. But you can see also is that it is more slanted, meaning there's more dispersion. So we looked at this, and so we've got a Peclet number of 750, 165, and then 34. And then this is NCSTRs of 16, which is 16 high or low? Well, that's the question, is what is plug flow? So the question you have to answer is with respect to kinetic modeling, okay? So if you have a plug flow reactor, here's the equation. If you have an NCSTR model, here's the equation. So the question is, when you're looking at kinetics, okay, how do you analyze your system? Well, here in the light blue, whether or not you assume a fixed bed model or a CSTR model, it doesn't matter. You're going to get the same results. Now, when you're down here in green and yellow, your fixed bed model is going to be very different than your fluidized bed model. So when you're operating a fluidized bed for kinetics, you got to make sure you're operating in around 60% maximum conversion, maybe even 80% capacity. If you've got 16 as your number of CSTRs in series, you can operate up to 60 or 70% and assume that it is back mixed, which is kind of interesting. So to conclude, microfluidized beds are suitable for kinetics. And these again, these was a microfluidized bed. It wasn't a large fluidized bed with large bubbles and things like this. Now, the other advantage of fluidized beds is that it's isothermal. That's approximately isothermal. And then solids are back mixed, which is a huge advantage of a fixed bed because all the solids have the same oxidation state. They all have the same deactivation rate. They have the same carbon buildup. And is gas and plug flow? We don't care if you're measuring the kinetics with 40% conversion. This sounds weird. Okay. Anyway, that was the conclusion. So this work, of course, was with my student Ariane Berard, and then we collaborated with Miguel Menendez and Javier Enrido at the University of Perrault.
Thank you very much, Gregory. Do we have questions from the audience? Ali, do you have a question?
Not really, I was actually clapping, but I may have a question for Gregory. Nice presentation. When you talk about the microfluidized bed, I assume you are scaling down the reactor. Do you also scale down the particles or?
That's a huge debate, okay? And everybody says I'm wrong, okay? I use the catalyst that I want to use commercially, okay? But Glixman and MIT and then the folks in Austria, they will actually change the particle characteristics. When I say microfluidized bed, I am looking at 10 millimeters about. And what I'm interested in is the kinetics, okay? If I'm doing hydrodynamics, then I might have to do the scaling. I still don't want to do it, but people suggest that you have to do it. But not for the kinetics. The kinetics, you got to use the catalyst that you want, okay?
Super, thanks.
Thanks, Harvey. Thanks.
Do we have other questions? Oh, Federico has one. Go ahead.
Actually, it's just a curiosity to comment for students. You showed that was very interesting about measuring kinetics in fluidized bed. Is there an influence of the reaction order or the reaction itself?
Okay, you will have noticed that the model that I use is a first order model, okay? When you get into kinetics where you have multiple and parallel and different orders, then you have to be more careful. Excellent comment. So that I don't know, I don't have a rule for you, but simple kinetics, use it. And I guess the other corollary is that if you want to understand the kinetics, put in a reaction, okay? But then you'd have to start in what Ali said. Okay, now I got a reaction, but how do I scale that? Now, do I have to change the particle characteristics for scale up?
Super, thank you so much.
Great question.
Okay, thank you very much, Gregory, for your presentation. Can you please stop screen sharing?
My question was about, is it possible to manage the hydrodynamics inside the reactor to be close to plug flow reactor or mixed?
Okay, so the question was, how do you manage plug flow in a working operating reactor? And Steve Jordan that came from DuPont, he was let's say, one of the prime driving forces. He said you have to have 30% fines. If you don't have 30% fines, then your bed is bubbling and you're going to get big. So fines is the answer. Now, he got a $135,000 let's say bonus because people tried to put in breaker bars into the reactor, and he said it doesn't work, it doesn't work, it doesn't work. And they lied to management, and he proved that they didn't know what they were doing, and that's why he got a bonus. So breaker bars, according to him and a lot of people, don't work, and the only way to control the plug flow behavior of a bed is with fines, meaning 20 to 45%, 20 to 45 micron particles, 30%. Great question.
Okay, super. Thank you very much, Gregory.
Thanks.
Can you please stop screen sharing? Okay, the next speaker is Professor Anil Mehrotra from University of Calgary. He will be talking about heat transfer experiments with a cold finger apparatus to demonstrate analogy between wax deposition and ice deposition processes. Professor Mehrotra, the floor is yours.
All right, let me share my screen. Okay, 1 minute. Okay, thank you very much, Alma. I appreciate it. So my presentation is like Gregory's presentation. It's not really the kind of talks you have been listening to. I'm going to talk about using a simple apparatus, a cold finger apparatus, to demonstrate analogy between wax deposition and ice deposition processes. There is a long history behind this study, and I will talk about it a little bit. My co-author is Sina Hassani, and the work was carried out at the University of Calgary. This presentation is based on a paper we published recently in Energy and Fuels, which will have more details. So let me begin. So it is, I'm going to talk about a simple experimental apparatus to study and compare wax deposition and ice deposition processes. And the results will show, both experimental and modeling results will show that the two processes are similar. Then we will look at predictions from Stefan's moving boundary problem formulation. We will use that approach for both systems, and we'll show that both systems are well modeled by this approach. And then we will conclude that the solid deposition from waxy mixtures is also a thermally driven process, which is very important. So let me start. Those of you who are not familiar with this type of crude oil, I'll just give you a brief background. So first of all, crude oils are complex mixtures of hydrocarbons. Everybody knows that. Waxy or paraffinic crude oils are a special class of crude oils that are multi-component mixtures of mostly N-alkanes. And what happens with these crude oils is waxes or heavier alkanes, they crystallize from oil and deposit on cooler surfaces. So as the temperature of the oil is decreased, crystals, waxy paraffinic crystals come out of oil phase. It is a major and expensive flow assurance challenge. Estimates are that every year it costs about $1 billion to the oil industry to tackle wax deposition. And this picture kind of shows you what messy situation you can get into. There are clear disagreements in the mechanism for wax deposition. So although people have been working on it for 4 or 5 decades, we still don't have an agreement in terms of how we can describe wax deposition. In the next slide, I'm going to I've written some keywords that one should look at. There are 3 temperatures that are important in dealing with such crude oils. But the most important for us for this presentation is the wax appearance temperature, which is measured while cooling a crude oil, and it indicates the temperature at which first crystals appear in the sample. Several mechanisms have been proposed. Heat transfer is the one we are looking at in the presentation today. There is molecular diffusion and at least 8 or 10 other mechanisms people have proposed. So molecular diffusion approach, so why we did this study is described here. So molecular diffusion or mass transfer approach is the popular approach. It is the basis for commercial software packages that are sold by companies like Schlumberger. However, it has many weaknesses and inconsistencies, and it has been questioned, and it is being questioned even more seriously now by several groups in Italy and Brazil, myself, and other places. Our many previous studies have validated the heat transfer modeling approach, which involves partial freezing of the oil for wax deposition from crude oils. And we have tested it in hot flow, cold flow regimes, under static conditions, under laminar flow conditions, under turbulent flow, using flow loops, using cold finger apparatus. And every which way I look at this problem, and I'm convinced more and more that it is a heat transfer problem. So if that is the case, then existing software packages are starting at an incorrect point. So the whole software, and that probably is the reason companies are making money out of the software, and it's difficult for them to admit that their starting point is incorrect. So anyway, so if this is where the motivation for this study is. If the same heat transfer modeling approach could also be applied to the freezing of pure water, then it would further validate heat transfer approach for multi-component wax deposition. So pure water is single component. Maybe I'm jumping. Okay. So let's talk about freezing of a liquid. In phase change from liquid phase to solid phase, a pure single component liquid will have a well-defined freezing point temperature. In the absence of another diffusing species, single component, the solidification of liquid will be described solely by heat transfer. There cannot be any mass transfer because there is no other diffusing species. So there is no molecular diffusion, only heat transfer in the transformation of a pure single component liquid into solid. So if the same mathematical modeling approach could be shown to apply equally well to a multi-component mixture, then the wax deposition process can be concluded to be a heat transfer process also, just like ice formation. So this slide gives you basic steady state equations that are used in heat transfer approach. There are 4 thermal resistances. We talk about the flow of thermal energy. And this has been kind of not looked at seriously in the molecular diffusion approach. So this approach can explain a lot of properties of the deposition process. And we have shown this repeatedly in the literature. So this is the approach. It explains everything. Okay, we are focused on unsteady state phase transformation. Now, in the molecular diffusion approach, they actually use Fick's first law of diffusion to model unsteady state deposition. Okay, which is Fick's first law, as you know, is for steady state. So so for unsteady state phase transformation, we have used Stefan's moving boundary problem formulation, and this approach is useful for time-dependent phase change problems in which the location of the moving boundary is a function of time and space. This approach is good for modeling freezing and melting processes, quite popular in the metallurgical industry. I don't see too much of this application of this in chemical engineering literature. Interface keeps moving as more and more liquid is converted into solid, and the same approach can be used for melting of a solid into liquid. Because there is latent heat of phase change, it creates a heat source or heat sink at the interface, and that creates a discontinuity in the temperature profile. So that is something that comes out of the mathematical analysis. Anyway, so if you use this approach for in cylindrical coordinates for the freezing of pure liquids such as water, these are the equations, basic equations. Okay, there is a equation to describe heat flow in the solid phase, and there is a thermal energy balance at the interface. And these equations look simple, but solving them numerically is a little tricky. But we use MATLAB to solve these equations. In the good old days, my first PhD student working on this problem actually used Fortran, and it worked, okay? So it can be modeled, and we have explained this in many papers before, okay? So if you look at wax deposition, now you have a multi-component system. You don't have a freezing point temperature anymore. Instead, you have liquidus temperature and solidus temperature. and the temperature at which phase transformation will take place will be somewhere between liquidus and solidus temperature. In our approach, we have taken wax appearance temperature to be that temperature. And we have confirmed that from experimental studies. Otherwise, the equations are very similar, except that instead of thermal diffusivity of a pure substance, we have a modified thermal diffusivity of the deposit, because the deposit has both liquid and solid phases in it. Remember, we are between the liquidus temperature and solidus temperature. So it's neither pure liquid, not pure solid. It's a mixture of the two. Okay. Otherwise, equations are very, very similar. Experimental apparatus is pretty straightforward. This is what on the right-hand side, we have this, it's a simple heat exchanger basically. And the exposed copper surface is where the deposition takes place. Coolant flows through the cold finger. This cold finger is dipped into a liquid bath from which we are studying deposition. It's agitated vessel, stored in a larger container, cooling, cold maintaining conditions, and so on. So there are other peripheral equipment, baths and data logger. I'm not showing all that here, but basic concept is quite simple. It's a simple heat exchanger that you dip into the liquid reservoir. There is another approach for studying wax deposition, which is the flow loop approach. We have used that, a bench scale model. There have been some research groups that have used very elaborate flow loops, but it's not necessary in my opinion. For materials, for ice deposition, we use distilled water. For wax deposition, we created a synthetic crude oil by mixing a multi-component solvent shown on the left-hand side here in this GC analysis. And on the right-hand side is the multi-component wax. So we have multi-component solid wax dissolved in a multi-component liquid mixture. And we used a concentration of 10% mass percent wax in the solvent. Design of experiments, we tested all kinds of variables for different water temperatures, different agitation rates, deposition times from 30 seconds all the way to 8 hours. And similarly for wax deposition, only one wax concentration, different cooling temperatures, and so on and so forth. Okay, so quite a few experiments were performed. Now, these graphs show the agreement. And of course, I forgot to mention, there is a lot of calibration involved, especially in determining the heat transfer coefficient, because existing correlations for heat transfer coefficient would not work for our geometry. So we have calibration experiments and so on. Anyway, so the results, the symbols are experimentally measured deposit mass per area. So it's a mass per kilogram per meter square unit. And on the x-axis, we have deposition time. And the curves are predictions from the Stefan's moving boundary problem formulation that I showed before. So in all cases, you can see that the agreement between data and the predictions is very good. And so ice deposition is well described by this approach, the moving boundary problem approach. And different sets of results, varying oil temperature, or liquid temperature, both varying, both of them, and so on. So we tested it out in different ways. Now, the results for wax deposition, we have done many other measurements, and we have tested Stefan's formulation. It works very well. So I'll show you some results for wax deposition. The same kind of thing, okay? So again, symbols are experimental results. Curves are predictions from the Stefan problem. And again, look at the agreement is very, very good. And just a couple of notes. In modeling, in the heat transfer approach, we take interface temperature to be wax appearance temperature throughout. And the deposit that you get And let me, I forgot to highlight this. Let me go back to the previous slide. Okay, so if you look at the picture on the right-hand side, it shows you ice deposited on the cold finger, okay? And this ice is quite transparent, okay? Let me go to the next one. Here, the deposit that you see, the picture is not because it's out of focus. It's a fuzzy, it's translucent, it's not transparent, because wax deposit is a two-phase mixture, because we are working between the liquidus temperature and the solidus temperature. So there is liquid trapped in a matrix of solid crystals, basically. Okay, so that's what, and that's what happens in real wax deposition cases as well. Okay, so this slide shows you comparison of both sets of results. Solid squares are data for wax deposition. Hollow squares are experimental data, and we have plotted deposit mass as a function of the oil temperature. And look at the trend. They're both, first of all, there is good match. And second, the trend for both cases, both experimental results and model predictions, they're very, very similar. So what we are seeing is the two processes, wax deposition and ice deposition, are very similar, okay, are practically identical. I mean, there are differences in properties which make these differ, but the trends are very similar. Okay, so overall, I can conclude that the two deposition processes have many similarities. The predictions from the same, essentially the same mathematical modeling approach, they match the data quite well. Now, for ice deposition, we are looking at a single component, pure system, only heat transfer. There is no mass transfer or no molecular diffusion involved in the ice formation from pure water. The same approach applies to wax deposition, which is a multi-component system, and only looking at heat transfer considerations, we are able to describe the wax deposition process equally well using the same, essentially the same modeling approach. So what I'm concluding here is that there is really no need to invoke any molecular diffusion considerations when we talk about wax deposition. And of course, this study also demonstrated how a simple experimental apparatus and a simple technique could be used for achieving meaningful results. I want to thank the funding from NSER, from my department, and from my university for carrying out this research. Thank you very much. If there are any questions, I'll be happy to answer them. If you need any of if you have any questions later on, you can send me an email. If you want any of my previous publications, copies of them, send me an email. I'll be happy to send you those reprints. So thanks again for listening to my presentation.
Thank you very much, Professor Meratra. We're a little bit behind the schedule, but we have time for a very quick question, if we have any from the audience.
I don't think we have enough time, unfortunately.
Okay. For all the attendees, please feel free to contact Professor Meratra in the chat, and I'm sure he will be happy to reply to your questions in case you have any. So let's move to the last speaker of the session. What? Inan?
Sorry, even for the one in the room, if you have questions, I can just write them in the chat here. Just
yeah, exactly.
Yeah. Okay, thank you.
So we have one last speaker for this session before the very short coffee break. Please welcome. I hope I will not mispronounce her name. Xiao.
Hi, Xiao.
Hi, Xiao Wu, sorry.
Yes.
So he will be talking about pressure fluctuations. The floor is yours.
Yes, can everybody hear me? Yeah.
Yes.
I think it's good. Okay. Right. So good morning, everyone. Very glad to present the in this experimental method series, and the topic of this work is about the pressure fluctuation, but here I'm more generally about the pressure measurements. So the paper is still under drafting, but the highlights here shows the key points that will be covered in the paper and also this talk, but we will come back to these at the end. I think it's more clear at the end. So measuring pressure already becomes a strategic requirement throughout different stages of online process supervision, safe operation, efficient production, and some quality control. So pressure, as I say here, is already become most essential state variables to measure, as it can reflect some of the performance of the reactor and also the behavior of the process. So in general, the pressure can be quantified mainly in three different forms here, as you can see the figure on the right here. So depends on the device and the applications. It can be expressed at absolute, a gauge, and a differential pressure. So the absolute pressure expresses the difference between the measured pressure and also the absolute zero pressure. And also gauge pressure is the difference between the measured and the local atmospheric pressure. And also the differential pressure is the difference of the pressure at two locals of locations of choice. The signal can be either positive or negative, depends on the application. Right, so nowadays we use these electronic pressure sensors more often because they provide improved performance and also allowed really fast and continuous measurement and control. So these electronic sensors are mainly diaphragm type and also integrate some of the electronics to translate the formation caused into measurable electric signals. So to differentiate them, it's common to categorize the transducers as voltage output device, and also transmitters as the current output device. And it can also be classified based on the sensing techniques. For example, here you have a piezo resistive pressure sensor, which the supplied pressure will stretch the piezo resistant elements here, and then cause the variations in the resistance of the resistors mount here. And also you have these piezo pressure sensor. The pressure act on these elements fabricated of piezo electrocrystal material here, and such as quartz or ceramic, and that will produce the voltage across to it. And also here we have these capacitive pressure sensor that my slides froze somehow. Sorry, I have to restart it again.
No problem. Try to screen share again.
Yeah. That's just my problem. Yes. Some reason. Yeah, do you see my screen again?
Yes, we do.
Go to the page I have. Yes. So here we talk about this capacitive pressure sensor. You have one of electrode here, and then the sensor measures the capacitance change over this distance by the strength of you put on the diaphragm here. Right, so for chemical production and operation involve flow or multi-flow systems, they can make good use of these pressure measurements. So simple application involve, you have a set point comparisons to maintain the sufficient hold up of your solids or liquids, like what shows here. You can measure the difference of pressure between the bottom and the top, if you know the bulk density of the material, and then you use this equation to calculate the how high of your loading. And of course, in the other way, if you know the loading, the height of your loading, then you can use this equation here, and also to calculate the average bulk density of your material. Of course, this measurement is not continuous. You can do per hour, per day, or even per week. It's part of the comprehensive interlock. But when the pressure is sampled at a sufficient high frequency, at the time resolved the pressure fluctuations is more insightful into the hydrodynamics. So typical methods that involves such as the calculation of the standard deviation, and also cycle time, which is the number of cycles of this fluctuation across its mean, and also frequency domain analysis that includes the power spectrum and transient power spectral density, and also wavelength method, which you can decompose your signal into representative wavelength at different frequency scale. And also one which was discussed many years ago, there was a state domain analysis. So you can use the pressure fluctuation signal to reconstruct a tractor, which is a fingerprint for each of the chaotic system. And also you can calculate chromograph entropy and so forth. So later I will focus on the first two, the time domain and the frequency domain analysis. So this network shows that pressure measurement already apply in the wide field of chemical engineering. So here we sample around 4,000 articles over the last 4 years. You can easily spot some of the classic the typical words you find in chemical engineering. That's the like temperature, the heat transfer, and absorption here. So clearly, this technique has been widely used in this field. So here I show example that reports in the work of Professor van Neumann a decade ago. And so they demonstrate the different analysis techniques that are available to understand the pressure fluctuations. So here they put particles which are fluidized under 4 different superficial gas velocity to attain the different bubbling states. So the figure below shows the corresponding power spectrum of 4 different bubbling regimes. So for the single and exploding bubbling regime that you see, these two graph actually shows it behaves like a underdamping oscillator. You have these clear peaks at these frequency range. And if you move to multiple bubbles here, you say this still shows underdamping, but with more strong underdamping actually. So you have a clear mode of peak here with in the range of 20 to 40 radius per second. So if you further increase your flow rate, you enter these transport conditions, and you show these are highly damped curve. So you use this technique, you can easily identify the regime changes between the fluidized bed. And of course, the standard deviation can also identify the change in the fluidized regime. That here shows when you increase the superficial gas velocity, you're entering from the bubbling regime to the turbulent fluidization. So you see these peak quickly decrease. And also you have, they also show that you can identify the defluidization. So here they put a step reduce in the superficial gas velocity at t equals 50 seconds. So you can see here, if you measure these standard deviation, you see these standard deviation quickly drop to the allowed level. But for the absolute pressure, you still maintain its level for another 2 minutes. So these provide a use for the early detection of the defluidization. So although nowadays these sensors are greatly reliable and robust than ever, but of course the installation and the operation can yet lead to uncertainties and errors that can fail your measurements. So before the measurements, one should always check more general issues that can encounter in the measurements here. So proper arrangements actually need to be done, such as adjust the zero offsets, and also place your sensor away from these high temperature and the corrosive, even the mechanical vibration environment, and also away from these electromagnetic emissions, because they will interfere your measured signal, and also you have to put some filter for it, or a filter for these unexpected pressure shock. And also, if you find your measured signals is significantly lower than you expect, and there might be some leak and also clog in your tube. So of course, the arrangement for pressure measurements has to be done also specifically for the application you applied. So here, example is for the bubbling bed. You probably need to be careful with the prop, where to put your prop, and which has to be avoid or mitigate disturbing your system hydrodynamics. And also, if you use a tube, this tube has to be small enough to avoid residence effect, also big enough to avoid damping. And also, the stance has to be as short as possible. And also, if you want to prevent the contamination from the particles, you have to put fine wire mesh on the entrance. And also, you can use some constant gas purge around it. And also, you have to be careful with the sampling frequency, because these typical hydrodynamic events happens at below 10 Hertz. So here we think 20 to 40 Hertz is already good enough. Right, so measuring pressure is already routine and robust for industrial applications, but understanding these pressure fluctuation signals is still really difficult, and especially to mapping them to the corresponding hydrodynamics event. So in parallel, we have these tomography techniques that were developed for originally for the medical research, but here we show these like X-ray tomography, MRI, and also many talks in this conference mentioned about the capacitance volume tomography. All of these has been shown that can use for analyze the system hydrodynamics, especially for a gas-solid fluidized bed. And also in recent year, they have improved the in their time and the space resolution. So we think if we can couple these two techniques in the lab scale, we're definitely to facilitate understanding of these pressure fluctuations. And later on, we use the knowledge learned that we can apply to a large scale, and then make these routine pressure measurements as more powerful and insightful for the industrial applications. Yes, so I would like to conclude here. So we show that the pressure measurements, a successful measurement actually requires careful selection and also arrangement, even the calibration of the pressure sensor. And also pressure fluctuations has a lot of really nice use, and such as they can indicate a regime change and indicate early detection of the defluidization, and other paper report they can even find out agglomeration and channels, so forth. And also we would like to couple with the pressure fluctuation, pressure measurements with other techniques, and then we will definitely that will definitely help to understand more about these pressure fluctuations. So, okay, that's it. Thank you for your attention.
Thank you very much for your presentation. It was insightful. Unfortunately, we are very behind schedule, so we don't have time for a question, but please remain online, and people will, if they have questions, they will be sending their questions in the chat. Okay?
Yep. Yeah, sure. Thank you.
Thank you very much. So we don't have a coffee break, and we start directly with the second session for this morning. And I'm actually the first presenter of the second session. So let me screen share. Two. All right, can you see my screen? Okay, so hello everyone. My name is Dalma Schipati. I'm a PhD candidate at Polytechnique Montréal, and today I'll be talking about high performance liquid chromatography. Let's start with some highlights. This technique is basically a separation technique, and it is separation is based on functional groups interaction between the analyte and the adsorbent material. There are several separation modes available. Reverse phase is the most common. So reverse phase is non-polar stationary phase and polar mobile phase, and we also have ion exchange and size exclusion, which is useful for polymers. Sorry, it's not. Okay. HPLC can be also coupled with several detectors. The most common ones are UV-Vis and refractive index, but also MS and other techniques are quite useful for polymers, light scattering, for example. The retention time is inversely proportional to the flow rate of the mobile phase, and specifically for reverse phase HPLC, it is inversely proportional to the concentration of the organic solvent in the mobile phase. HPLC is a very common technique, and in 2019, Web of Science indexed almost 9,000 articles with HPLC in the keywords. So as I mentioned, HPLC is a chromatographic technique that separates the analytes based on the interactions with an adsorbent material, which is called the stationary phase. And it is the stationary phase, it's the heart of the chromatographic system. The stationary phase retains and elutes molecules at different rates based on the interactions taking place in the columns, which can be electrostatic, hydrophobic, or you can also have orientation, induction, and dispersion forces. Depending on the strength of these interactions, the stationary phase retains analytes rather than allowing them to travel with the mobile phase and elute more or less rapidly with time. The retention factor, K, is the ratio of the time compounds elute from the column versus a reference compound that elutes at time 0. So in other words, K represents the time the stationary phase retains a compound versus the time it would have eluted if it had no affinity for the stationary phase. Analytes that have a higher affinity for the mobile phase, so low K, elute more rapidly than those that are strongly retained by the stationary phase, so at a high K. As a consequence, analytes that absorb and elute at distinct rates flow through the column at different velocities. The flow rate of the analyte is directly proportional to the flow of the mobile phase and inversely proportional to Ki according to the nearest distribution law. This is what a chromatogram looks like. So you have retention time on the x-axis and the signal of the detector on the y-axis. And when working with chromatographic techniques, it is important to optimize the analytical method in order to have the highest possible resolution, which basically describes the separation between the peaks of two components. So in this case, I and I+1. And for symmetrical peaks, resolution is basically the difference in retention time with respect to the average width of the peak at half peak height. So resolution increases with difference in peak retention time and or when peaks are narrow. These ensure, in quantitative analysis, the signal between the two peaks returns to the baseline, which is called the baseline resolution. And the fact that the signal goes down ensures the complete recovery of each analyte. The stationary phase plays a crucial role on the resolution. The material of the stationary phase affects selectivity, which has actually a greater impact on resolution than the particle diameter. And columns are selected based on their physical chemical properties and their compatibility with the analyte. Ideally, the stationary phase composition is similar to the molecules in question. The properties of the stationary phase that you need to select accurately are particle shape and size, and porosity and pore diameter. In terms of particle shape, spherical particles are more efficient than irregular particles, and particle diameters of 3 and 5 microns provide the best resolution. There are columns with smaller diameters, but they are for more specialized separations, and they have a higher efficiency of resolution, but they do tend to clog more easily. Besides the bead size, porosity and pore diameter impact efficiency because they affect band broadening and loading capacity. So non-porous packings prevent the stagnation of the mobile phase within the pores, and therefore you have better mass transfer. However, if you have pore deficiency, you don't have a lot of surface area and the loading capacity decreases. So ideally, the pore size should be at least 4 to 10 times the hydrodynamic diameter of the analyte, so it doesn't clog the pores when it flows in the column. The length of the column is sample and separation methodology dependent, and longer columns have higher separation efficiencies, but the analysis takes more time, so it becomes more expensive because you're also using more solvent. The column chosen for the separation process determines the mobile phase that you use. The retention factor varies with the concentration of the organic solvent. And here I have an example of isoproteron. It is a fertilizer. This is an analysis done on C18 columns, so non-polar, with a mobile phase consisting of water and acetonitrous, so polar. And you can see here that a lower percentage of organic solvent yields a higher resolution. Also, selectivity depends on the nature of the organic solvent. Generally speaking, polar solutes prefer polar mobile phases, and the columns releases them more quickly. So this is the case for reverse phase chromatography. However, non-polar solutes interact preferentially with the solid materials, so they are more retained. Here I have an example with resorcinol and vanillin. Resorcinol is more polar than vanillin, so the values you see on the graph are their dipole moment, and the resorcinol is more polar, so it prefers to stay in the mobile phase, and therefore it elutes before vanillin, which is less polar. Increasing the temperature in HPLC has a similar effect as small particle packings. So at room temperature, columns reach the upper pressure limit of the chromatographic system. And when you increase temperature, you reduce the analysis time, you enhance the resolution and selectivity. So when you increase the temperature, the viscosity of the mobile phase decreases. And I have an example here. I have the same example with the same molecules I showed before. So it's resorcinol and vanillin. And when you increase the temperature from 25 to 50 Celsius, you can see that the peak shifts and the shape changes. So in the case of vanillin, the peak width decreased by 19% and the peak height increased by 22.5%. So this leads to shorter analysis time and higher resolution, efficiency, and also selectivity. Moving to the applications, as I mentioned earlier, Web of Science core collection indexed more or less 8,900 articles only in 2019. It is, if you think about this number, it's relatively low compared to X-ray and SEM and other techniques. But this technique is pretty common. So we analyze only the keywords, and we estimate that the number of papers that actually include HPLC in the experimental section is at least an order of magnitude higher. We have 4 different clusters. HPLC is here you see the first one. HPLC is used quite a lot to determine the phenolic content. Then it is also used for combined with the mass spectrometry. It is used for validation, stability, and in separation. It's a separation technique. And then in the third cluster, you see that HPLC is mentioned in papers involving degradation and water. And eventually, we have a cluster including in vitro and purification, and also some biosynthesis and derivatives. Several factors contribute to uncertainty in HPLC, but one of the most important ones is sample preparation. And people underestimate the importance of preparing the samples correctly, but this is what ensures consistent and reproducible results. So sample preparation includes dilution and derivatization, for example. When samples are too concentrated, they saturate the detector. So I have here an example, and you can see that the signal goes back to the baseline, well, actually a little bit below the baseline. And those are not two peaks, it's just one analyte. So if you dilute, this is what happens to the signal. Another example of sample preparation is derivatization. This is an example of an acylation of an amine, which makes the amine more thermally stable, and it also increases the sensitivity of some detectors. Sample preparation includes also making sure that the sample is stable at the analytical conditions and that it is compatible with the solvent. And also the analyst has to make sure that the sample is liquid and does not contain any solids, because otherwise the column would clog and it would generate noise and alter the retention time. And this is actually one of the most common mistakes that beginners do when start using HPSC. And they normally select the wrong filter. So there are several membranes that are available, and they all have different applications. For example, in your lab, I'm sure you have cellulose acetate syringe filters, and they're very common, they're cheap, and they're used for aqueous solutions and biological samples. People use them on a daily basis, but they don't know that they dissolve at low pH and in several organic solvents. So if you work at this condition, you might want to go with a polypropylene filter. Other sources of uncertainty are related to the detector that is coupled with the HPSC. Each detector has a different limit of detection and sensitivity. UV-Vis, which is one of the cheapest and hence the most employed detectors, it has a sensitivity that ranges between 10 power minus 11 to 10 power minus 12 grams. And it is selective for molecules that actually absorb between 190 and 750 nanometers. Another common detector is refractive index. The sensitivity is in the range of microgram per liters, but it is only used for isocratic separation and for compounds that are not visible under UV-Vis. Another common detector uses mass spectrometry. The sensitivity ranges in the lowest limit of detection is in the order of picomoles, but you can also see molar masses above 100 kilodaltons. And light scattering is less sensitive than other techniques, but it's very useful for polymers. And normally the higher the molecular weight of the polymer, the higher the resolution, the sensitivity. The detector response to analytes is calibrated with standards, and you normally validate the chromatographic method by doing a design of experiment and varying all the factors that could be affecting your analysis. Moving on to the perspectives, HPSC represents the largest product segment of the laboratory analytical instrument market. And ever since its introduction in the 60s, the trajectory of HPSC has been towards the use of smaller particles at higher pressure to achieve faster separation. And this trend has greatly accelerated over the past, I would say 6-7 years due to the introduction of particle sizes that were below 2 microns. So HPSC development also goes together with detector development. And modern detectors, they're becoming more sensitive and they generate lower noise baselines. It is pretty common now to use gradient elution. So you vary the composition of your mobile phase throughout the analysis. This helps you separating your compounds better and also in a faster way because you save solvent. And this is particularly useful in the pharmaceutical industry when you have a lot of compounds with different polarities. Also, another important aspect of, well, it's a science, chemometrics. It's a science of extracting information from chemical systems using disciplines, for example, like multivariate statistics. And this type of analysis is frequently overlooked, but it actually helps improving the sample throughput in liquid chromatography. And these type of studies are useful to implement the curve resolution, the peak shape, shape, and also to significantly reduce the level of the chromatographic resolution that you need for accurate and precise analysis. So to conclude, HPLC is a flexible and versatile technique. As I mentioned, the retention time is inversely proportional to the flow rate and to the concentration of the organic solvent. This is valid for reverse phase chromatography. The peak shape varies, is directly proportional to the concentration of the organic solvent in the mobile phase powered 2. And core shell infused core packings, so packings with very low particle sizes, so below 2 microns, improve resolution and throughput. And sample preparation and solvent selection determine the resolution and reproducibility of the analysis. This concludes my presentation. Thank you very much, and let me know if you have any questions. Okay, I see a question. Yep.
Hello, Dalma. This is Deepak Kripalani from NRC. One key question, and this is in regards to your VOS viewer plot that you showed the interactions and where a lot of the development is occurring in and more of science is being produced. I guess my real point is that most of those applications on flavonoids or even in the water treatment area, they're highly focused on UPLC type work. Is that correct?
We plotted, sorry, I hear background noise. We only plotted the word HPLC. So this is an analysis of all the articles indexed in 2019 with HPLC in the keyword. So yes, it could be HPLC, and smaller particles, they're actually more efficient. So 2019, like the technology is pretty advanced. So most of these articles, they do use UHPLC, yes.
Thank you.
So if we don't have any more questions, I would like to introduce the next speaker. We have again Federico Galli, and right now today, well, in this session, he will be presenting gas chromatography.
Hey, thank you very much. Do you see my screen?
Yes.
And do you see my presentation?
Yes, perfect.
Yes. Huh? So can I start?
Yeah, sure, go ahead.
Oh, okay, super, thank you so much. So again, hello everyone and welcome again. In this presentation, I'm going to try to give you a general overview about gas chromatography and why this technique is so important for chemical engineers. The article on GC has been submitted and is now under review. So today I will show you a preview of the content of the manuscript plus some other stuff about calibration to give you just a mega picture. So almost every chemical lab is equipped with at least one GC. With the GC, you measure the concentration of an analyte in a solution, either in liquid or a gaseous mixture. For example, you can use GC to determine the amount of saturated fatty acid in an oil or the amount of methane and CO2 in a biogas sample. Among the most important parameters that you can play with to increase the separation efficiency, there are carrier velocity, temperature and temperature ramp, and the column type itself. In the last 2 years, more than 16,000 articles reported GC, which is more or less about 20% of all the papers published in chemical engineering in that period. Also today, I will show you 3 calibration methods that you can use and which is the best depending on the type of your sample and your sample mixture. So what is a GC? In the end, the GC is an oven. It's an oven that hosts one or more chromatographic columns. The oven controls the temperature and can operate in an isotherm regime or with a temperature ramp defined by the user. The columns are usually of 2 types, packed meaning that the column are filled with the porous substances, and separates column by mass separates analytes, sorry, by mass transfer, like for example the mold sieve columns for permanent gases, or capillary columns, in which the stationary phase is either a gel or a solid adsorbed on the column walls. In this case, the column is able to separate substances injected thanks to their different affinity between the stationary and the analytes, the stationary phase and the analyte. For example, an interaction mechanism is based on polarity. The more polar the analyte is, the stronger the interaction with the stationary phase will be, and therefore the longer it will take to that particular analyte to elute. The column inlet is connected to an injector. There are two main types of liquid injector: vaporizing and not vaporizing. As you can imagine, in a vaporizing injector, the temperature of the inlet is kept above the boiling temperature of your sample, which is usually diluted in a solvent. So let's say temperature above the boiling temperature of your diluting solvent. And in the injector, the sample completely vaporizes, and the inert gas, which is the carrier or the mobile phase, takes your sample volatilized into the column. Vaporizing injector may be split or splitless. In split mode, only a fraction, let's say less than 5% of the vapor, again depends on the configuration, enters in the column. The rest of the vaporized sample is vented out through a purge valve. This technique is suitable for concentrated samples and when dilution is impossible, for example, for essential oils analysis. Splitless injection on the other end transfers basically all the samples into the column. This method is suitable for trace analysis, for example. On the other end, non-vaporizing injection or on-column injector do not vaporize the sample. The temperature of the inlet is way below the boiling temperature of your sample, and therefore you inject liquid. It's then the temperature ramp that vaporizes your sample that enters into the column. Talking about the carrier gas, most setups employ either helium or argon, nitrogen or hydrogen. So these four gases are the main used, depending on the objective of the analysis, of course. Also, depending on the detector installed, you may require other process gases, such as air or hydrogen as a fuel for FID detectors. Also, makeup gas stabilizes detector signals. The most common detectors are the flame ionization detector, FID, which employs a hydrogen-oxygen flame to ionize eluted substances and measure ionization current variation, and is the best towards the quantification of CH bonds, so hydrocarbons, for example. TCD, TCD, which is a thermoconductivity detector, consists of a Wheatstone bridge that senses the change of resistance associated with the heat loss from the filament into the gas containing the analyte. It generates a measurable voltage change, and checks it against a reference voltage. TCD responds to, let's say, almost all compounds, as long as there is enough difference between the CP of the carrier and the analyte. Finally, MS is a mass spectrometers, quantify the M over Z, the mass to charge ratio of the analyte, and it is a universal technique. So here I propose you a little scheme concerning chromatographic separation. We already talked about a little bit during the HPLC presentation. We are considering a capillary column and two analytes, the green and the red. The stationary phase is represented in yellow, and the mobile phase transports the analytes from the left to the right. At the injection, the red and the green analytes are mixed, but the red one interacts with the stationary phase, and in the stationary phase, the diffusion of the analytes is reduced compared to the gas phase. The time at which the peak reaches its maximum is called the retention time. And after some time, you see that the green analyte is less retained, so it exits first. And then after some time, also the red one will produce its peak. Since the red analyte interacts way more with the stationary phase, its diffusion is way bigger, and this produces the effect of what we call peak broadening, meaning that the longer the interaction of the analyte is with the stationary phase, the larger will be the peak. And this is thermodynamics, and this effect is inevitable. You can try to do something with it with the temperature ramp, but still it will exist. Similar to distillation theory, we can define the efficiency of a separation with the number of theoretical stages or theoretical trace n. If we assume that the chromatographic peak is a Gaussian distribution, which is reasonable for most of the analytes, the number of the theoretical stages is proportional to the retention time and inverse proportional to the peak width. There is also a constant that depends on which peak width you choose. The constant is 5.54 if you take the 50%, the width at the 50% height. H instead represent the height of the theoretical plate, and is basically n divided by the column length. So we want to minimize this number to get the maximum performance out of the column. There is a lot of theory regarding mass transfer in GC, and you will find it in our article, both for capillary and packed columns. In general, H is the sum between the contribution of a molecular diffusion and mass transfer in the mobile and stationary phase. And it has a minimum for a certain carrier velocity. High molecular weight carriers, such as argon, have lower H minimum compared to light carriers such as helium. However, this minimum is obtained at a lower carrier velocity, which results in longer GC analysis, because it takes more time for the carrier to take out your analytes. And this is why, in general, light gases are preferred to speed up the analysis at the expenses of the separation performances. Gas chromatography is employed almost everywhere. So again, this is a Voss viewer map based on text. That you will find in the title and the abstract of recent article. The bigger the circle, the most frequent the keyword is, and the more close the words are, the most related they are. So blue cluster represents the articles on methods. The Journal of Chromatography and many other published new methods to improve components detectability in complex matrices, such as contaminated air samples, for which the analyst must use a solid phase extraction and GCMS. The yellow cluster, okay, relates to the analysis of the essential oils or biological samples. In this case, special columns and GCMS are employed. The red and the green cluster are related to two other fields of application, biomedical and water and biomass analysis, respectively. So a survey among chromatographic analysts, so professional, revealed that more than half of the time of the analysis is dedicated to sample preparation. We were talking about this also during HPLC talk. These practices involve sampling, dilution, derivatization, concentration, and any other operation necessary to prepare the sample before its injection. Data management takes 27% of the analyst time, and only 6% of the time is taken by the analysis itself, by the GC itself. Also, the survey asked the practitioner where, according to them, errors originate. And as you can see, 30% of the error originates from sample processing. so from a human error. How do we avoid all these sources of error? Well, if you can afford it, you can, and if you have a more or less standard sample preparation, you can purchase a robot to prepare your samples. Otherwise, you will need to rely on statistics, so repetition and a good calibration. In this slide, I would like to talk indeed about the calibration of your analysis, which is the most important part of this talk. How do you calibrate your GC to quantify the concentration of analyte in a solution? So in general, a calibration correlates the response of an instrument. In the case of the GC is 99% of the chromatographic area, or the percentage of the area, versus a measurable characteristic of your sample. And 99% of the case, we are talking about mole or mass fraction of the analyte in your solution. Once the correlation is known, you can calculate the concentration of the unknown from the response of the GC. So depending on the complexity of the sample, there are different calibration methods. And the easiest is the external standard method. You want to use this method when the analyte concentration does not change a lot in your sample, and when there is no interaction effect in your sample. For example, air quality measurement or CO2 concentration in the air, for example, are suitable analysis for this external calibration. What do you do with this method is that you prepare different standard solutions with known analyte concentration. You inject them in the GC and you measure the response. So you build your calibration lines, which report on the y-axis the response of the instrument, and on the x-axis the concentration of your analyte. A straight line passes from the origin of the axis, because when there is no analyte, there is no signal. And simply by measuring the response of the instrument of your unknown, you can back calculate the concentration. When your sample shows a certain degree of variability, like in chemical reaction, when your analyte is your reactant, so it goes from a certain concentration to 0, you want to measure your concentration, so its concentration varies with time and can reach the 0. You may use internal standard method. The method consists of adding to all your standard solution a constant amount of internal standard, which is a different molecule from the analyte, but has same chemical structure and independent retention time. In this case, we will measure, so we add the standard everywhere, and we will measure the okay. In this case, we will measure the ratio of the chromatographic area of the analyte and the internal standard versus the concentration of the analyte. Since the peak areas depend also on the quantity injected, this calibration method eliminates the injection error and is suggested for liquid analysis, especially when you use manual injection. Finally, if you have a complex matrix with many components and noise, the standard addition method is what you need to calculate the concentration of the analyte. With this method, the analyst prepares sample solutions of constant amount and adds to them different amount of the analyte. So in the first case, in the internal standard, we added a standard that was was similar to the analyte, but with a different chemical entity. In this method, we added the analyte. So for example, if we're measuring phenol, we are adding different amounts to our sample of phenol. With this method, so the calibration curve will be a line that will not pass from the origin, because also the first sample contains our analyte, in our example, phenol. However, extrapolating back the line, we can to the 0, we can calculate the analyte concentration. So this method is the best when you have a very complex matrix, for example, wastewaters or air contaminants. The future of GC is bright. Research is active on the synthesis and test of new stationary phases to improve the quality of complex analysis. Automation eases sample preparation and analysis, reducing errors and cost. And finally, miniaturization, made possible also GC on a chip, will permit the injection of way smaller samples. To conclude, we say that GC is omnipresent, the technique is easy, reproducible, inexpensive. Choose the calibration method according to the complexity of your sample and your injection type. Check split and purge flow rates or cut column if peak fronting or tailing. We didn't talk about this during the presentation, but there is a huge discussion in the paper. So I'll refer you to that. Thank you so much. If you have any question, feel free to ask.
Thank you very much, Federico. Do we have questions from the audience? I don't see any questions. Well, I would like to move on to the next speaker since we are a few minutes behind schedule. Please welcome Masoud Heri Nejad, PhD candidate, University of New Brunswick. Are you there, Masoud?
Yes, sir. Yes,
okay.
I'm there. Okay, I'm going to.
Okay, perfect.
Started,
so Masoud will be presenting developing a fast screening technique to find the optimum gas adsorbent, which is on point after the presentation on GC. Perfect, we see your screen.
Thank you very much. Okay, so thank you very much for the introduction. Also, I would like to say thank you for the previous presenter for very interesting talk. Yes, I'm Masoud Heri from University of New Brunswick in Fredericton, and Dr. H is my professor supervisor, and the title is Developing Fast Screening Technique to Find the Optimum Gas Adsorbent, and I'll tell you what this technique is. So I should say that we used zero-length column chromatography for equilibrium absorption studies, and I predicted gas absorption isotherms and also calculated total gas absorption capacity as a metric for ranking of adsorbents. So as an introduction, gas absorption has been studied and been gaining popularity as an alternative to the conventional distillation or cryodistillation as well as absorption operations that are right now in use, and that's because of its smaller energy consumption and also improved environmental footprints. I mean, for example, in absorption, we have these solvents, wastes that are sometimes not very environmentally friendly. So, but when it comes to gas absorption, the adsorbent, the material, the solid adsorbent material, characteristics are very important before we can decide whether it's the process is going to be efficient and selective regards to separating the gas mixture. So that is why we usually need to do some gather some data about texture, about thermodynamics or kinetic behavior of that material. I mean, what are we looking for example? We're looking for a specific surface area, pore size distribution, pore volume size. Also, some characteristic curves are very helpful, like adsorption isotherms or breakthrough curves. So just an example, let's talk about adsorption equilibrium measurements. For example, we want to get adsorption isotherms. And traditionally, we have two different methods which are equally giving similar results. One of them is the volumetric method, which is based on the changes in the pressure inside the sample, the manifold. The pressure change gives you an idea that amount which has been absorbed, and you can calculate the amount at each point, how much absorption has occurred, and move on to the next one. This is a step-by-step process which you are stepwise increasing the pressure. A gravimetric absorption is more direct method because you just measure the weight. I mean, as the solvent, as the adsorbent is getting more absorbed at higher pressures, so you see it becomes heavier. So the uptake is monitored again in a stepwise fashion. So these conventional methods are good, very rigorously, but they are time-consuming and sometimes expensive if you want to do it somewhere else. So they're not suitable for rapid screening if you have a large number of candidate adsorbents and you want to make a choice. And so besides, there's also another thing about the minimum sample requirement for these methods to be reliable, to give you reliable data. They are usually in the range of 80 or 800 milligram range, which is not desirable, for example, for the people who are synthesizing MOF samples. Their samples are very small. And I have this issue with that they say that, okay, sorry, we cannot do, it's not enough for our tests. So this means that we need some, also not only faster, but less complicated methods. And zero-length column chromatography is one example that can overcome this issue. So what is zero-length column chromatography? Well, it's basically a reverse chromatographic method, which was first developed for kinetic studies, for measurement of diffusivity. But now it has been extended to equilibrium studies as well. We call it zero, not because it's not zero actually, because the column length is very, very small. It's actually a Swidger-Log union. So where you have a single layer of pellets or powder inside of it, and which is sandwiched between two sintered plates. And then because of the small size, you have negligible mass and heat transfer effects, no back mixing. It's a kind of well-mixed system. And then another difference is that here the zero column chromatography is based on desorption rather than the uptake. The desorption curve data are important for us. So based on my description of ZLC system, so the total mass balance could be summarized as this, where the VS refers to the volume of the solid adsorbent, and the VG is the gas holdup, and the F is the flow rate of the purge gas, and the C is the concentration in the gas phase, and Q is the adsorbent concentration. Now, well, also we should, if you want to model this further, you need to have an idea of what the isotherm probably looks like, especially if it's in the low concentration region. So if you assume that it's a linear isotherm, so the desorption curve equation could be described like this. It's going to be a line with this slope, where if you have already run a blank test, you can directly get the value of the Henry constant. And if, for example, you can just expand this to a different type of isotherm. For example, if you're assuming a Langmuir isotherm, then the desorption curve looks like this. It's not going to be exactly a line, but could have some intercept. So if you solve this for the general case, without consideration of what the isotherm looks like, also you can do that. This is for the very general case. And this equation tells two things. It tells us that it helps us to calculate the full adsorption isotherm, and also gives an idea of the total capacity. So it indicates that if you plot the normalized concentration change versus FC divided T divided by VS here, or instead of VS, we can use the mass corresponding, the mass of the adsorbent, and compare, look at the area under the curve. It can give you a very good, at least even qualitative idea of which adsorbent has a higher capacity, because it is related to it. So before I show you some curves, I also show you the experimental setup, what it looks like. So a small amount of the sample is loaded inside a Swidger-Log union, which serves as a sample cell. The sample is first regenerated using the flow of inert gas, could be argon, helium usually, at elevated temperatures to remove not only the moisture, but also the residual impurities and the adsorbents. And then it is exposed to a flow of single or multiple component gases, which are diluted with a carrier gas, actually, an inert carrier gas. At low flow rates, usually about maybe 5 milliliters per minute or lower. Then after a brief equilibration stage, then the flow is switched to the purge flow, where the carrier gas removes the adsorbed material, and then using, let's say, a suitable detector, such as the mass spectrometer, you can monitor the desorption until it reaches the baseline. And this is what the setup looks like, the one I have. And you can see that we have a GC, but the GC is basically what we need about it is the oven, and we don't use a column. We have a sample cell, which is usually horizontal, not vertical. Vertical, and then this is the VC valve that changes between this flow for equilibration, where you have for example, in this case, we have CO2, which is diluted with helium, and the MFCs helps you to get the right concentration. And then this goes through the vent, and also we have this mass spectrometer here and the flow meter. And then once you are ready for the desorption, you just shift into this pure helium, and the flow rates, of course, should be the same. So this is an example, for example, for the CO2 at 1% at 30 degrees Celsius. And I've just done this plot of the concentration change versus FT divided by M. And you can see that, okay, for these different adsorbents, so some of them, the area under the curve for some of them is higher than the other ones. And about the blank, I should say that usually you can choose a material like rock wool, which has, you know that it's not absorbing, it's a non-absorbing material, just for reference. So doing the integration, you can already get this visually ranking of the adsorbents. For example, for CO2, which, for example, in this case, has a higher capacity. So for storage applications, for instance, and also the isotherm, you can get it, and it also can be shown here. It is also just is in accordance with what we found with the desorption curves. You can go to another gas, for example. You can do methane, for example, and do the same thing, and you see that for the same adsorbents, the ranking is different. Also, the isotherms look different. Another one, for example, olefin, again, the ranking are different, and they have different isotherms. So in the end, what you have is that you can have these data. So these are very valuable, because if you are just looking at storage of a single gas into your adsorbent, for example, in CO2 storage, that is usually very popular. So you can just focus on this one. But if you're interested in selectivity, if you want to purify, for example, you have a mixture of paraffin and olefin, and then you want to make a decision about which one, you have to see that it shouldn't be a good adsorbent of both components, but it should be a strong adsorbent of one and a weak adsorbent of the other one. For example, here you see that for A, it has very low absorption towards this olefin, but towards this paraffin itself. So you can make a decision. Or if you have methane, natural gas, and then it contains some methane, some CO2, then okay, you can make your choice. So what could cause a source of uncertainty or induce errors in your measurement? Well, you have to make sure that you have done sufficient pre-treatment. And why is it important? Because of the small sample size, it is very sensitive to humidity. So you have to take care of that. Also, sometimes incurrent baselining or blank correction also can cause errors, but then with practice, you learn about it. For example, for the case of strong adsorbents, blank correction is not a big thing. But for weak adsorbents, this is important. Also, the detector response time. Well, if you're using FID or TCD, well, they are quite fast. With mass spectrometer, it is slow, but with the choice of, let's column capillary column choice, you can even achieve comparable sensitivity. And finally, dead volume. You have to make sure that the valve, the stream change valve, is as close as possible to the sample cell and also to the detector. So in perspective, we're going to say that, for example, calculated adsorption isotherm curve, determined adsorption capacity and selectivity, and I did all these experiments in a matter of 1 or 2 days, which is very quick compared to what would have been done if we want to do it with rigorously those conventional systems. So another thing is that I want to emphasize, because of the small samples requirement, we can have a small gas consumption during the experiment and shorter measurement time. And which I mentioned is important if your sample size is also small. And also the thing is that when you do this integration, you can, instead of points, you can get an idea of the complete adsorption isotherm. And you can do this during only a single run from a single desorption curve. So you can also supplement this system with molecular simulation results, which can help you. I'm looking into that as well. Thank you very much for your attendance. I will be taking questions.
Thank you very much. Do we have any question from the audience? Let me see if I have questions. I don't see any question. We are a little bit behind, so let's move to the next presenter. Thank you very much. Thank you very much, Masoud.
Thank you.
So the next presenter is Abbas Gambari. I don't see him online. Is he presenting live?
Dalma, I don't see Abbas either. And he was supposed to present, but I don't think he's online.
Okay. Let me see the waiting room. There's nobody there.
I haven't heard from him that he was not available or something.
Okay. Well, Charles is the next speaker. He's already there, so we can move to Charles' presentation. Yes, we can hear you. And then if Abbas joins the meeting, he can present after Charles.
So that's this one. Okay. So I don't know if you can see me. Yeah.
Yes. So please welcome Charles Burrell, and I would like to take the opportunity to congratulate you for your best thesis, PhD thesis award that you received yesterday by the CIC. So congratulations.
Thanks.
And he will be talking about contact angles today. So please go ahead.
So hello everyone, thanks for taking this presentation on contact angle, which is also based on the eponymous article in the Canadian Journal of Chemical Engineering. And I will give you some example based on one of my PhD paper in Langmuir. So the first question that comes to mind when you think about contact angle, it's basically what's the shape of water. So you may answer me that it's a very famous movie, but if you're more engineer-minded, you will start to ask me more questions. So is there gravity, is it in motion, is it pure? And by asking all these questions, you will acknowledge the fact that contact angle and the shape of a liquid is a balance, a complex balance of forces. So it will depend on surface tension forces, gravity, viscous forces. And what we call contact angle science actually refers to a situation in which the surface tension forces are 100 to 1,000 times stronger than gravity, and where surface tension forces in here are 10 to the power 5 times stronger than viscous forces. We are speaking about steady in here and quasi-steady states. Usually transient states are not described by contact angle equations. So if I just consider a drop of water in here on a PVC card, and that I have a look at water molecules, what are their interaction? What we have, okay, that a molecule of water in the middle of the drop in here will form liquid-liquid interactions. As it moves towards interface, it will form, for instance, air liquid or a liquid-solid interactions. But all these interactions do not have the same strength, meaning that there is energy to be considered here. And what we call the shape of a liquid, basically, it's the optimization of this energy. And it leads to the creation of surface tension forces, so on interfacial forces that applies on each interface. And if I try to apply this force balance in here as a free phase line of contact, meaning really the perimeter of the drop on the surface, I will have one interfacial forces for each of my interface. So solid gas, and solid liquid. And if I project this force balance on the plane of the surface in here, I will get Young's equation, which was derived as early as 1805. And so in this equation, you will see, so the cosinus of an angle that is actually the contact angle in here. So you may think, okay, it's done. I have the contact angle, but it's not that simple, because although in an ideal case, you have a single contact angle value, which is a thermodynamic value, in real cases, you will have a wide range of contact angle available with a maximum or advancing contact angle, a minimum or receding contact angle, the difference in between being the hysteresis. And the reason why you have all these possibilities is because, well, if you consider energy, again, any small feature on the surface will create some metastable states in here, in which your system can just be like stuck. So you have a maximum contact angle available, a minimum one, and it's not easy to determine which one is actually the global minimum. So any kinetic or thermodynamic features can create these states. For instance, evaporation or swelling of the sample, and thermodynamic, we will speak about roughness or chemical heterogeneity. So in order to perform contact angle measurements, you will need to use Young's equation to use a certain number of variants that will be able to account for non-ideal behaviors. We are speaking about Wenzel model or the Cassie-Baxter model in here. And finally, eventually you will want to reduce your number of parameters by using equations that are actually described in the article. So let's speak a bit about the application for contact angle. So this is a VOS viewer graph of all the keywords that are used alongside contact angle in article. So it concerns roughly 4,000 articles a year. Besides generic keywords in purple, we have a field that is just focused on developing wetting science. One field in material engineering where they try to fabricate advanced surfaces, so thin film, coating, new deposition methods. You have a field in here in polymers, adhesion, and biomedical. The link between biomedical applications and contact angle actually arises from the fact that you can often predict the antibacterial properties of a film based on its contact angle with water. And finally, there is a whole field linked with nanomaterial, nanoparticle, and their separation. So how do I measure a contact angle? Well, it will actually really depend on the morphology of the sample, be it a micropowder, a flat surface, a plate, or a fiber. In here, for a reason of time, I will focus on optical goniometry with a cecil drop or advancing receding contact angle measurements. So in ARCA, advancing receding contact angle measurements, what we do is that this is a needle of a syringe. We will inject liquid on a surface, on your substrate, and we will grow a drop, measure its contact angle while it grows, stops, suck in the liquid, and measure the contact angle as it recedes. So that's the advancing and the receding contact angle. So how does it work? Well, first you have a few preparation steps. You need to select the method, prepare your sample, select the prop liquid, and calibrate your system. In my case, I was working with cellulose nanocrystals in here, which are on phyphilic nanoparticles. I'm lucky because just using water, I can actually cast them in the form of a very flat film in here with roughness in the range of 10 to 20 nanometers, meaning that optical goniometry is a good choice in my case. For the prop liquid, I have to choose a solvent that will not redisperse my particle. So water used for solvent casting, for instance, is not a good option in my case. So I choose ethane glycol or diodomethane. And then finally, you will have to take different calibration steps, being like just the angle of the camera, is there reflection, whatever. You can find this step in the article. Then finally, you can go into the acquisition of your measurement. So as we said, in the first step, you will deposit a drop, so the volume increases, you stop, you suck in the liquid, you stop. And these parameters, again, you have to choose them based on the force balance we discussed about. So I choose the maximum volume based on the bond number, the injection rate based on the capillary number in here. And so that's what it looks like in here. So in the first phase, when I inject the liquid, I will increase the diameter of the drop while keeping a roughly constant contact angle. In a second phase, when I stop, so nothing happens, then I suck in the liquid. And what's interesting is that instead of just receding, we will first see a decrease in the contact angle in here. And only in a second phase, we will see a small receding of the drop on the surface. And so on this graph in here, so which is real data, okay, yeah, but then the camera is here. That's the point. Okay, so what we have is that we can see on this graph everything that goes wrong, that can go wrong in terms of uncertainty. So the fact that we have a negative positive trend in here is linked to the fact that we have a gravity effect. So despite choosing a low bond number, we still have a gravity effect. All the small bumps in here are linked to the roughness and the chemical heterogeneity on of my sample. And finally, I'm able to check whether I have a kinetic phenomena or not. That's the whole actually of phase 2 and 4. I stop injection and I want to see if the contact angle is stable. So if ever I have swelling, it will absorb and so it will decrease. And so based on this graph, I can measure so the advancing and receding contact angle and their uncertainty. I can measure the hysteresis. Now that I have quality data, I can basically try to attribute the hysteresis. In my case, if you look in the article, we linked it to the unphilicity of the particle. Then you can try to perform some modeling to calculate the surface tension. And finally, perform some extra interpretation. So in our case, we saw that depending on the casting protocol we choose, spin coating or oven casting, we had various films with different contact angle. As a perspective, I would like to tell you that the complexity of the contact angle measurement method is directly a function of your objective. If you just want to characterize the wetting behavior, is it hydrophobic, super hydrophobic, you can stop quite early and the method is really easy. However, if you want to calculate surface property analysis, attribute hysteresis causes to roughness or whatever, you will need to go further. To calculate surface tension parameters, so estimate the free surface energy and our adhesive property, it will be even more complex and require several liquids. Finally, for derived application, you will need to add a few other extra steps. So as a conclusion, we saw that the method and feasibility for contact angle measurements is directly dependent on sample morphology and properties. We saw that contact angle science relies on the complex force balance and on multiple phenomena, which means that interpretation must be supported by other techniques, such as atomic force microscopy, particle size distribution, swelling tests, etc. And finally, one of the reasons why contact angle is used despite all its flaws is that it is one of the most feature-sensitive techniques available with an angstrom size resolution. So you can basically see anything with it. So thanks for your attention. And if you have any questions, I will be happy to take them.
Thank you very much, Charles. Great presentation. Do we have questions from the audience? From Polytechnique, no questions?
Yes.
In your slide 10, you show us how the angle is changing depending on the phase from the injection and the finishing of the sucking of the At the beginning of the presentation, here you show that the angle is changing because of gravity forces prevails. But at the beginning of the presentation, you were also talking about that many forces contributes and also the viscosity, etc. Did you contribute? How do you think that maybe the viscosity is also contribute in changing of the
Actually, the way through which I can control the influence of viscosity is through the capillary number. So there is a kind of an experimental correlation that says that if your capillary number is below 10 to the power of 5, then you will be able to make the estimation that the contact angle, like the dynamic contact angle, is equal to the static contact angle. So that's something you can really see, you know, when you stop your movements. If I had viscous forces, then when I stop my injection, I will still see a small change afterwards. Like the viscous forces keeps influencing my contact angle. And so if basically when I stop, it stops, it means that I have well done my job of calibration. I have chosen the right rate of injection. And in my case, the influence of gravity, it's really, you can understand it that when the drop grows, you will have more weight on the liquid. And so this angle in here is slightly smaller than this one. And that's just the effect of gravity, but there's basically nothing you can do about it.
Okay. Do we have another question from Polly? No, I don't think so. Thank you very much, Olga, for your question, and thank you, Charles, for the presentation. I still don't see Abbas. Is he, any chance he is in the room at Polytechnique? Maybe he's presenting in person?
No, he's not. Sorry.
Okay, thank you.
So thanks Anna, for chairing the session, by the way.
Yeah, you're very welcome. My pleasure. So I don't see Abbas. That's a pity. So I would close this session, or actually maybe I will leave it open in case Abbas shows up. Thank you for attending the experimental method session. It was very nice attending all of your presentations. So I feel like we all did a great job. So thank you very much. Well, everybody's leaving, so I guess we can close this meeting. Inan, are you still there? Hello.
Hey.
Yeah, one speaker is not showing up, so let's just close this session. Okay.
Okay, thank you so much.
Thank you very much, Inan. Bye.
Bye.